a humanoid. And you see that the workstations are primary workplace for the workers or the robots, and mobility is largely not required. But mostly we need two arms and two delegated hands to be able to do all of this. For me, as a student, under Matt Mason some years ago, was very fascinated about dexterous manipulation, but really haven't get a chance to really do much. Now today, we now understand from neurosciences, from physiology, what we are capable of doing with our hands, especially when we do the fine touch of assembly by feel, by hand-eye coordination. But we have not been able to get the robots to mimic or to acquire the skills, especially the skills that a very delicate young workers are able to do. So what are the technology components that are missing? One of which is what we are now focusing on, that is trying to figure out how to learn from humans. We know that reinforcement learning is a very powerful tool. Imitation learning has some achievements, but for the human dexterous operations in the faculty, you were not able to really observe a last fine process of getting things done. That is imparting forces and energy to get the components in the right place with efficiency. Most workers do this very quickly, and it's not strenuous, but in the end, it's very tedious. So they will not like to work for 8 or 10 hours a day. But what would be the tools for us to get robots to learn of this? Of course, we are trying sim to real, imitation learning, and learn from demonstrations, all these two techniques in the laboratories. But to me, we are really lack of knowledge of human data, especially the touch and feel and tactile sensations that we use quite extensively in our skills. And there are databases or there are platforms for collecting data, for training robots to do dexterous manipulations, but the tasks that they are able to do or the data available for the tasks are very, very much limited. Grasping is one big category, insertion is another, but fine dexterous manipulation is not much there. So I will just say that one of the technology that is lacking is the tactile sensing. Although we know there are a lot of research in the soft skin on tactile sensing, but for any dexterous manipulation without the tactile capability, you will find it very difficult. This would be a case for a young girl who lost the skin sensation for touch. So there are sensors and would help us, and we have built a particular type of sensor based on optical measurements that will give us more detailed information about pressure distribution. Especially, we are able to categorize the modalities of tactile sensing and make use of that for robotic manipulation. We're able to integrate them within the fingers of a robot hand, and we have done some work that to be able to make use of them for robot learning. But in comparison, very quickly, with the tactile sensing capabilities of the human skins, we are very much short. We already know that there are 4 types of receptors, and they are distributed over multiple places in our hands, and our sensors are far, far away from these capabilities. And there are a lot of questions. Do we need 4 kinds of receptors? Do we need all this information? And if we do, how do we achieve them? Especially, how would we be able to acquire the signals from a human hand, 4 types of reception signals, and use them to process or to teach our robots. And furthermore, in the last 10 years or so, we already know that finger schemes have memory about history of deformation. And history of deformation is used in the current process of manipulation control. And also fingers have computing powers as well. So there's still a long way to go to make use of AI. And what I'm trying to say is that robot manipulation skill learning is big task, and there's still a lot of room for engineering, not only for the people to do algorithms. Thank you very much.
Thank you, Michael.
Yeah, I'm joining our
Sorry that we do not have any time for
Thank you everybody for your patience while we sort out some technical stuff. So I just want to introduce Austin. This is Austin Kaburia. He's a student, Dean from Art University in Kenya, and he is also an undergraduate research assistant in data science and AI.
Hello, my name is Austin. I'll be presenting our work with my professor, Shira Omaina. Animals have unique gait and have signal perspective. Just a bit of background. Biodiversity is all life on Earth. All life from microbes to rainforest to monkey and how they attain an ecosystem balance. According to a report by the Worldwide Fund Nature, there's a 69% decline in this animal population the last 50 years from the 1970s. This is not good. And over 1 million species are on the verge of being extinct. This calls for an urgent action that is needed to stop the biodiversity loss. And one of the ways in the school, we have a camera trap. A camera trap is a camera trap that was deployed in the university's conservancy. Now, what a camera trap is, it's a motion-activated camera that is used to capture these animals, to monitor these animals in the wild, to try and be able to see these particular animals, to track their behavior, and also be able to estimate the population. One of the ways or the problem with using a camera trap to be able to count or to do this population estimation is double counting. When an animal passes the camera, then comes back again, you'd count it as 2 animals. They are not marked. But in the past, or people have done, this is a problem that has been there, and how they've been able to do it is they've been looking at unique patterns. A zebra, a giraffe, or a tiger, they're basically barcoded, where this particular, their coat patterns, you can be able to identify an individual animal based on just an image of this. But they're not effective for impalas or horses or animals that have just one similar coat pattern, which makes it a bit hard to be able to do this for them. And also another issue has been there are some that don't have unique patterns, like a rhino, but they look at the eye of this particular rhino, or the faces of chimpanzees, or the ears of the elephant, or tail of a shark. So we try and look for ways that can solve this problem for animals with similar coat patterns. We look to humans. Humans have a unique working style. this was shown by Johansson as early as 1973, where this study was a human would walk with point lights. And this particular point they have kinematic patterns. You could be able to identify this human being by how they're just walking across over time. And we try to do this for four-legged mammals. I believe the animals do have unique gait, and they should be able to, you should be able to re-identify this particular animal if you see it walk over time. And we started by building AlgePose, an animal pose estimation model, where we try and get the joint locations. The same, more or less, how the study started with getting the joints. We try and get the joints for the particular animal. You can scan the QR code to get started the pose model. How we did this was, okay, we started with AlgePose, but it is a bit hard to use the model to generate data. That was the idea, but we found a data set, different data set, TikTok data set that we could at least do some preliminary tests. And for this is an example of a horse and how we generate the graph of it. How we do this, the input is a video, and each particular video is made up of frames. For each frame, each frame consists of the joint locations, and we represent the joint locations as the skeleton of this, as a graph. And how we do this is each particular joint, we get the Euclidean distance between the two joints, and that becomes our edge weights, and the nodes are the joint locations. We do this for the entire video, and the result is on the and one of the things to be able to have some sort of preliminary test was rhythm arises from when you walk in a certain motion. You walk when you have rhythm when there's exchange of time, place, and energy. And we can be able to represent this rhythm as a signal. And how we do this, we use the Frobenius norm. For each particular frame, we generate an adjacency matrix. And for this, we compute the Frobenius norm for this particular frame over time. This generates a signal, this particular signal. And for this signal, we're able to see, one, the magnitude reduces over time, but this can be attributed, the animal moves further away. You don't have depth. We're using XY coordinates. The animal moves further away from the point of view where the camera is. The animal moves further away. That's the decrease in magnitude the distance from the camera. But we're also able to see some sort of repetition represented by the two rectangles for this particular animal. This signal is for this animal. We're able to see some sort of repetition that we can try and, or let's say, maybe it should work. Now, we tried to look for better ways to encode this data. And how we did this is, for each frame, we compute a normalized Laplacian. Vectorize this Laplacian for this particular frame, repeat the process for the duration of the video, then compute the average. This was supposed to be, are supposed to be the embeddings of this. We reduce this video to this space, this high dimensional space based on that. 304 and 308 is the same animal. 485 is a different animal. Before finding the average of this embeddings, of the average Laplacian, we tried and reduced to the 2-dimension, and 304 and 306 more or less clustered together compared to 485 to try and say that perhaps you can be able to re-identify this particular animal when you have two video, when it passes the camera and comes back again. That's preliminary. And one of the ways is maybe we'll look for ways to normalize depth. We try to build a bigger data set. We built a model to do that. And does this particular case, is it affected by the environment? Will it change? Will this animal change in a different environment? And maybe simulate the environment if possible, or find a better way to test that. Thank the team for the. Thank you.
So, a couple quick questions. How big was that data set, and about, on average, how long was each video?
Around the duration was less than 20 seconds. We had like 100 videos.
Have you considered kind of like maybe using that data set to kind of like generate like a larger data set by just basically creating multiple videos where you are splitting the existing videos, and then like 10 seconds videos, you can do like random crops of like 8 seconds to like 5 seconds videos, and then you also that additional kind of like augmented data to train those embedded. Because like maybe something interesting to try out would be, because fundamentally the video is like a sequence model, right? So maybe you can use the approach you use that for this norm approach, or the one that's solid there, to encode a single frame of a video to tokenize that, and then pass the sequence. Sorry, and then pass the sequence of the full video to a transformer. What you're going to get at the end of that is going to be an embedding that represents the whole video sequence. And so that is kind of like going to be your model. Maybe you can use like the architecture of GPT-2 because that's not too computationally intensive. And you train that and see if it gives you decent clustering in terms of like similar, like the same animal having like having its embedding be very close in the embedding space and be very disentangled from like the embeddings of other animals. Maybe that is something worth trying, because like transformers have proven to be very good at kind of like learning good embeddings, which are also kind of like nicely clustered. You have a lot of data. So for this idea, data will be your fundamental bottleneck. Maybe if you do the implementation on what you already have, maybe that will help.
Speaking on data, have you looked at using data sets that are already there that might be available? Because I think depth is going to be quite important to kind of consider in the analysis, because we'll have to kind of improve kind of some of the findings. So I think CNOSET or Alco's data has a bit of like that depth in there. Maybe see we'll have a lot more videos with depth with the work.
Actually, speaking of that, adding on to what she just said, maybe you can use data sets like that to pre-train a transformer and then fine tune.
So were you doing, were you using data sets where the motion capture and reconstruction of the motion had already been done? Because I noticed like the one with the horse was nice, but like, you know, you're losing parts of the leg to occlusion and things like that. So maybe something like Sina said, where there's the 3D motion that's already been done from like multiple cameras, you'd have a more complete picture of the animal. Or to what extent does it matter? How much of the animal do you need to be able to see to do this?
Okay, that was a problem. Start using, you see, just a small part of the animal, which brought noise, and maybe that will help.
Everyone, please can we thank. Okay, and I'm going to break for a coffee break, and we can be back at 10:30 for the next keynote. He is also a senior member of the ICRA and is a member of the South African Institute of Electrical Engineers. And one of his many research topics is in robotics control, and this is what he's with us today.
Yeah, good morning.
Hello.
Nice to speak after we've had something else to Right, so I'm sure by now most of you are suffering from information overload. Because over the past 3 days, there's been lots of information, lots and lots of information, and I'll try as much as possible not to overburden you. So I'll try to make my presentation short. So I want to share about robotics, human control. When I was asked to talk about control, I was wondering, what do I talk about? The history of control, and just give an icebreaker. Professors who are here, please don't be too hard on yourselves, like Bara said. If you've not written a book, don't be too hard on yourself. It's not that hard. Yeah, some of us are passionate about books, some people are passionate about journals and so on. So, robotics beyond control, shaping a smarter, more inclusive future. So my name is Elisha Didam Marcus from the Central University of Technology. All right, so I'm going to give you a brief history. I know most of you know already, but I'm just going to remind you, it's always good to look at history, where we're coming from. So we started with classical control, and now we're moving to AI-driven robots. And you may want to ask, what is control? What is robotic control? So robotic control is just trying to write algorithms to enable the robot interact with the environment. So you achieve that by using sensors, actuators, different sensors, actuators, cameras, and so on, to interact with the environment. So that's what control is. So I'm just going to give you a brief history of how control has evolved from the past, into where we are at the moment. So in the pre-20th century, we had early mechanical control, where most of the systems were using cams, gears, and pulleys. In the picture there, we have the Hero of Alexandria. So this was one of the earliest examples of control systems, where they used air pressure and water hydraulics to be able to control the system. And it was done by open loop control. So open loop means that you just give a sequence of events, and then you have the output. And then between the 18th and the 19th century, we had the Industrial Revolution and the rise of mechanical automation. It was around the time when the textile industry was booming, and Packard Loom came up with this complex design, where he used punch cards to design complex textile designs. So this Jacquard loom was a precursor to the Jacquard computer. And from then on, we began to see programmable early control using digital inputs. So it started from the Jacquard loom of 1801. And then came to the mid-20th century, where the first industrial robot was patented, called the Unimate in 1954. So the Unimate basically was an electrohydraulic system or robotic system, and it had basic form of storage, and also was controlled based on a sequence of events, which we call open loop. And it was at that time we began to see the emergence of feedback control. We started seeing PIDs coming up, and that was also used in the automotive industry, where we had spot welding and automotive, applied in automotive industries. And then there was a rise of digital control in the 70s to 80s, where we started seeing microprocessors and PLCs. And then digital control was becoming popular. So some of you have used PLCs. People still use PLCs for process automation. And between the 70s and 80s, we began to see the rise of state space control, where we use models to describe the robot dynamics in terms of vectors and matrices. And some of you must have used linear quadratic regulators to check whether your system is overshooting and things like that. And we also had Kalman filters for optimal and state estimation. And then in the 1990s to 2000s, we started seeing advanced control systems. So we started seeing sensor integration and machine vision, which is more advanced control systems. And we started seeing cameras and proximity sensors. And we started seeing real-time feedback. Of course, this came with the advancement in computing power, right? So the more computing power we had, the more we were evolving in control systems. So we started seeing algorithms like edge detection, where you can carry out control, on the device or on the inter-device, small devices. And we could do pattern recognition, feature extraction. And then we started seeing adaptive and process control, introduction to model predictive control, where you're able to predict future state of the robot and optimize the control. And then we started seeing real-time trajectory planning and adaptive, which is adaptive to changing environments. Yeah, so then between the 2010s and the present, that is where we are right now. We're in the era of AI and autonomous robotics. So we've seen the first speaker, Prof. Mutambara, talked about AI. We can't run away from AI. It's here to stay. It is here to stay. And it is driving, control systems. And now we're seeing AI-driven control systems. We can now fly drones and get feedback, video feedback in real time. And then we're also seeing improvement in machine learning algorithms, using deep learning, reinforcement learning for autonomous decision making, neural network controllers, which enabled end-to-end learning. And now we have drones and autonomous vehicles and collaborative robots. I'm going to share with you some of the work that we are doing that is in relation to some of these applications. And in the present era of autonomous robotics, we now see we have simultaneous localization and mapping. And of course, we're able to compute inverse kinematics very easily. I remember when I first did my PhD, I was calculating the inverse kinematics for a 6 degree of freedom robot. And I was using some software called Maple. And the equations it gave me was like 26 pages. So you can imagine being able to compute that on a computer. It's going to take a long time. And some of us did our PhD, And that's one of the challenges we have in Africa. Sometimes when we talk of Africa, we also have to look at where we're coming from. Some of us did our PhDs where we didn't have a robotic lab, but we're doing PhD in robotics. So you have to think out of the box. You have to, just create something out of nothing. And I remember I was running helter-skelter from my university to CSIR, and my supervisor was not keen on that, but I was running helter-skelter between, just so that I can see what they are doing there and then try to see how that relates to my work. So it's quite challenging in Africa. So when you see people who are into robotics, they may not be as astute as your Michelle Johnson from US, where they have all the labs and funding and so on. So we'll try to do what we're doing as little as we can. So I just want to speak a bit about the future robotic systems. So before that, I just want to talk a bit about your AI-driven robots. Just to give 3 examples, about ASIMO, Boston Dynamics, and PEMA. So these are 3 very popular AI-driven robots, and all of them use AI algorithms, advanced navigation algorithms, facial recognition, and so on, to be able to navigate and interact with the environment. So the future trends of robotics control, I'm just going to touch a bit on that, and then I'll go into what we're currently doing in our research. So cloud robotics is becoming something that is going to dominate future trends in robotics, where you offload your information or your control into the cloud, and then even your data storage and so on, you can take everything to the cloud, and then you compute everything, and then you deploy to the robots. So that can be applied in warehouse robots, autonomous delivery robots, large-scale robotic operations. However, there are some challenges of latency, because when you have to deploy in the cloud, you have issues of latency. Obviously, there's security concerns. So we've had challenges also with the issue of latency, deploying information in the cloud. And then internet connectivity is a challenge, right? So we all know how internet is in South Africa. Sometimes, like yesterday, I was trying to drive home, and I was depending on my GPS. And I was driving to the hotel, not home. And then my GPS just didn't come up. So luckily, I had people in the car who assisted me. So internet connectivity is a challenge. And then edge computing, of course, is different from cloud computing, because with edge computing, you're able to carry out your control or your computing on the device itself. Of course, with that comes reduced latency, improved real-time responsiveness, enhanced privacy, and so on. And this finds applications in industrial robots, drones, medical robots, where immediate decision-making is critical. And then we have adaptive and self-optimizing control. So the adaptive control, an example is your model predictive control that is able to optimize control actions in real time. Integration of real-time data from sensors, in continuous adaptation to changing environments. And of course, that finds application in autonomous vehicles, robotic exoskeletons, and advanced prosthetics. We've seen the presentation from Ryan. So some of these algorithms for their prosthetics. And also self-tuning controllers, where You automatically adjust the parameters based on performance feedback and try to enhance the stability of your performance. And then this finds application in industrial automation, where very loads and changing dynamics are common. And then we have quantum computers now. Quantum computers are a thing now. They are still evolving. So with quantum computers, you can solve complex optimization challenges much faster. So we foresee that in the future, this is going to play a very big role in robotic control. It's going to revolutionalize trajectory planning, multi-robot coordination, and complex tasks in complex decision-making tasks. So this is still in early stages with experimental applications in robotics and predictive control. Okay, I know I said I'm not going to say a lot, but yeah, just bear with me. I'm just I'll end. So swarm robotics is also something that we're trying to do in our lab, where we don't want to have a centralized control. We want to distribute the control across the devices as much as possible. And right now, with the proliferation of Internet of Things, it's projected that by 2050, we're going to have about how many billion connected devices. So a lot of devices are being connected into, across the globe. And some of these devices can be used, as data or as information for control. So swarm robotics is, of course, something that mimics social behavior. And the centralized control where multiple of us are able to work collectively. So you have your drone. So initially when we started with our lab, we were trying to do something like this where we have this decentralized control. However, when we wanted to purchase the robots, it was quite expensive. So we decided to improvise. So I'll tell you about that. So swarm robotics finds the applications in search and rescue. And there's a strong focus on communication protocols. Some of the challenges in robust coordination in noisy environments and being able to find global success rates where you have these individual devices that you're trying to control at the same time. And human-robot interaction is also something that is evolving. We've seen the presentation from Michelle about human-robot interaction, where you're able to assist the user in terms of rehabilitation and so on. So we're going to see a lot of this, and I believe most of you are beginning to work on human-robot interaction and collaborative control. And safety is a big issue when a human is involved. So this is a very strong area of research. Machine learning for gesture and voice recognition, application in cobots in manufacturing and so on, and force control and tactile feedback. So of course, because the human is involved, the issue of tactile feedback is also a challenge. So the example of the egg, you'll be able to, a human being can pick an egg easily, but if you ask a robot to do that, it's going to fumble. So you have to make sure you program the tactile control. Otherwise, you're breaking the eggs. So those kind of sensitive control systems are evolving. Of course, robots used in medical procedures where precise control is crucial. Okay, so nowadays we've seen medical robots where we use telemetry. They can carry out operation on someone, from a distance. So that requires strong precision, and also the force control has to be precise. So these are present and futuristic robotic control systems. And then you have the bio-inspired and soft robotics. Rian made a presentation yesterday on prosthetics. So the algorithms that manage deformable, flexible actuators for safe and adaptive interactions. So the use cases include wearable robots, delicate object handling, exploration robots, and navigate tight spaces. So soft robotics is an area that is also going to be very popular. Okay. Then there's the challenge of ethical and secure control systems. So when you talk about human-robot interaction, safety is number one. How do you get the robots to be trustworthy, to take after or look after your child, for instance? So we need those kind of robots, this kind of control systems, trustworthy AI, and explainable control. So the control system should be explainable. Now with ChatGPT, you can write codes, you can do a lot of things. It's great. So you should be able to create explainable, easy control algorithms that can be used for that are easily understandable. Ensuring that decisions are understandable and predictable. We also need to develop algorithms that are transparent and that can be audited for safety. So transparency is key. So most of the speakers here talked about in Africa, we work in silos, so we need to be a bit more transparent and collaborate more, because transparency is key for us to be able to move on and overcome some of those ethical challenges. Of course, cybersecurity in robotic control is a challenge. How do you ensure that your algorithms are secure? And how do you protect your robots from threats and hijacks, which can disrupt operations? So all these are open problems that need to be solved. Incorporating encryption, secure protocols, communication protocols, and IDS. So all these are ethical challenges that need to be tackled. So the future of advanced AI, adaptive algorithms, and cutting-edge hardware technologies means pushing boundaries. Okay? Now, pushing boundaries, especially for the African continent, we've had some of the speakers talk about Africa. So we need to develop our own solutions by pushing boundaries, sometimes working from nothing, almost think out of the box. And now in the age of AI, we cannot afford to work, in silo. You must be interdisciplinary in nature. So you must understand control, you must understand a bit of AI, you must understand a bit of, neural network or bio systems or, So there's no working in silos anymore. So we just have to work together. The civil engineers must come together with the mechanical engineers, with the occupational therapists, and so on to create and to push boundaries of what robots can achieve. Making them smarter, more capable of operating in complex and dynamic environments. Okay. All right, so now I'm going to talk about enough of the history now. I'll talk about a few of our research projects that we're busy with. So when I started my PhD over 10 years ago, this was the first robot arm that I worked with. So this is a flexible robot arm. Yeah, so here we were dealing with a flexible arm, and we were applying the principle of differential flatness. So differential flatness is a control algorithm that you take a nonlinear system and convert it to sort of transform it to a linear system. So we know that nonlinear systems can be difficult to control, right? So we're able to take create a fictitious output called flat output. That flat output enables you to apply your linear controls. So I put this here because this was the first robot arm that I worked on. So it was very interesting, and we were able to compensate for the flexibility in the arm. And then from there, we moved on to cooperative control. So again, let me give you a small story, how I came about cooperative control. So I worked on when I started my PhD, I was doing something on industrial robot control. So I was working on the 6 degree of freedom robot that I didn't have in the lab. Okay, so I was working from equations and kinematics and dynamics and so on. And then I wasn't getting anywhere with my research. So after 2 years of all kinds of research, checking the papers, and robotics is a physical thing. So I was distraught, and I approached my supervisor and I told him that this 6 degree of freedom is not working. Look for something else. So that was how I got into the flexible robot, and I did some conference papers on them. Of course, I couldn't do a journal paper because at the time I didn't understand a lot about control. Okay, so I was now trying to get a contribution for my PhD, and then I couldn't get a contribution from the flexible robot, and I couldn't get a contribution from the industrial robot, because the industrial robot, they are legacy robots. They are mostly used in industries, so they are not meant for research. So there wasn't much I could do with that. So I came up with cooperative control, to merge, the idea of having, what I've worked on for 2 years doesn't go to waste. So this is how I came about combining, the flexible robot arm with an industrial robot, because I already had the models, I've worked on them, and see how they can cooperate and do something. So this is how I came about the contribution for my PhD. And so talking about working from nothing, absolutely. So this is how we use the flatness technique. We developed the flat output. The nice thing about flatness is that once if you're able to determine the flat output for the robot, you can use that parameter to parameterize trajectory planning. And you can use that to generate trajectories. And the other robots, all you need to do is to configure the leader robot, and then the other robots will follow. You don't have to configure all of them at a go. So this is how I came about the cooperative control system. And then after my PhD, I started looking for how to make it physical. And I wanted to apply this cooperative control into, a lab setting with physical robots. And then I came across assistive mobility systems. That was how I started working on wheelchairs. So electric wheelchairs are like mobile robots. So I started thinking about how can I make these robots work together. So I came up with 3 ideas. The first one was using AI for diagnostics, because at the time, AI was emerging, and I was passionate about AI at the time. So, and also another story by the side was my dad had my late dad, he had dementia at the time. And at the time, we didn't know he had dementia because he kept forgetting things. Sometimes when I call him, he doesn't remember, some things. And so it took a bit of research to realize that he had dementia, because nobody in my family ever had that before. So that really got me curious. So at some point, he had to become wheelchair bound. So he couldn't do things for himself. He couldn't remember things. He couldn't move around. So that got me thinking, how can I help someone like my dad? That was how I came about assistive mobility, because we had to buy him a wheelchair. And I thought about maybe we can, use AI, maybe to diagnose some of these things before they happen. And we can also leverage sensor fusion for adaptability. Because now with Internet of Things, you can adapt, to your environment as much as possible. So an example from Michelle's presentation. And then communication. So my background, I actually did my master's in telecommunications, so I know a lot about communication. So I wanted to bring in all those skills. Again, trying to work from nothing. So trying to bring all those skills that I know I had to create something. So that was how we started the project on assistive mobility system. So this was a paper, conference paper that my master students published 2020. And it was a paper on the diagnostics. How do you use sensors to diagnose, some of these threatening elements before it actually occurs. So we started doing this work with the student, and then he came up with we were able to come up with a kind of framework. And at the time, we were building some sensor prototypes. We were focusing on diabetes at the time because diabetes was a challenge in South Africa. And we were developing some sensors that we can use to detect, using AI, predict, if, for instance, if somebody has a certain threshold of sugar in his urine, then you're able to know. So we were doing this work. Unfortunately, the students didn't finish. Again, another challenge in Africa. So he had a family to take care of, and he felt he was just. The masters was not funding him enough, so he went for greener pastures and he left. He abandoned the project, and unfortunately, we were not able to continue with this project, as laudable as it is. And then, in terms of the adaptability, I got a PhD student who started doing some work on shared control, and we're looking at wheelchairs. So wheelchairs are mobile robots. Okay, so communicating, in a smart city scenario, of course, sharing information via the cloud, and that information. So we had a scenario. We were trying to look at the user on the wheelchair communicating with the wheelchair in a local environment, and then the wheelchairs communicating with each other in a global environment. So it was a two-level control system that we're looking at. And of course, that information will be shared with clinicians and physicians in real time to be able to assist the users. So we're looking mostly, especially people who were cognitively impaired. So people who were not able to, like the people with dementia and autism and so on. So those are the kind of people we're looking at. Okay, so yeah. So yesterday you must have seen Dr. Daniel's presentation. So he came up with multi-sensor fusion architecture to combine LiDAR and camera images to create a bird's eye view mapping of the environment. So this was part of the idea we had about adaptability. So I'm sure you saw in the poster that he presented, where now we're able to capture images in real time and process them with less computational environment. And so this work, we're actually working on a patent on it, and hopefully we're looking for investors who are into LiDAR technology. So if you know somebody in BMW or Mercedes-Benz who wants to invest in LiDAR technology, we have something for you. Okay, so, and then the third part of the, idea we had about cooperative control of assistive robots was having them communicate with each other. So Paul is here. Paul is a PhD student also. So he's busy with the interaction of the wheelchairs with the environment using digital twin. So he's going to present more on that after this presentation. And then we decided to be, a bit, so what is the word? We decided to look at wireless power transfer. So because there's a lot of computational requirement for wheelchairs. I know this is a manual wheelchair, but there's a lot of computational requirement when you use electric wheelchairs. So we thought that we can actually design some kind of wireless power transfer. So there's a PhD student who is working on this currently. It looks impossible, but like Mandela said, it's always impossible until it's done. So looking at just like you have your self-driving cars, to drive to somewhere and charge, we want to look at the possibility of being able to charge these wheelchairs wirelessly on the go. Okay, so we move on now to the semi-autonomous control design. So we call it semi-autonomous because we know that autonomous systems are difficult to achieve, right? So we don't want to say autonomous systems, semi-autonomous systems. The idea behind the semi-autonomous systems is to be able to assist people who are actually on wheelchairs, who have cognitive impairment, who have little control on the wheelchair. So be able to design technologies that will assist them. So this is what we've done. We've retrofitted the wheelchairs with sensors and cameras and screens and Jetson nanos and so on to be able to get the wheelchair ready for operative control. And this is an example of the control. So here we're trying to, the wheelchair are trying to communicate with each other. They're trying to communicate with each other. Share information. The idea is that if the wheelchairs can share information and communicate, sometimes synchronize, will be several applications. I'm going to show you one of the this type of communication and shared control is required. All right, so I couldn't get most of the videos. I couldn't. They're quite large, so I'm going to play the video at the end. So the project that we are busy with, I was privileged to meet an international collaborator, Professor Eric Monacelli from France, and we started discussing about wheelchairs and how we can bring inclusivity into people using wheelchairs. In 2018, and we came up with a concept called dancing wheelchairs. So the dancing wheelchairs, like you saw in that wheelchair, the wheelchairs, people can use them to dance using gesture control and so on. So Eric came up with the name vaulting. Okay, so vaulting. So it's an innovation in mobility, arts, and sports. So this collaboration is a collaboration involving 5 continents, 5 teams. In 2023, we had a show in Japan, and we had another show in Canada. No, the one in Canada was moved to next year. So we had a show in South Africa, which I will play the video for you. And then we also participated in the National Arts Festival. And then we went to the Paralympics, the recent Paralympics in Paris. And then we also have another show in Brazil. So the idea of the vaulting is about rehabilitation and adapted physical activity. So vaulting is a new adapted body engagement tool with multiple benefits for post-trauma rehabilitation and sport. So the idea of this is that people who have gone through trauma or are wheelchair bound will still be able to have a social life, which also creates independence, because not all people on wheelchairs are invited to shows, right? Especially in Africa. So we thought that it would be a good idea to have a show for the wheelchair community. And I'm going to play something like that. So this idea is great because it brings art and science together, and you'll see it from the people's faces how excited they were, to attend such a show, and then see how the robotic wheelchairs are able to move by themselves, and they're able to dance with them and so on. So the objective was to offer, of course, physical activity and leisure activities, fair sport, dance, and art. So on the website, if you go to the website, which is www.vaulting.org, you see more information about that. So in France, we were able to, we did a show in France. And like I said, we did a show in collaboration with TUT. The TUT had a dance club, and we did a show called Unlimited at the National Arts Festival, the recently completed National Arts Festival. And I'm going to play you a video on the event that we had at CUT. Okay, so on the website, there are some testimonials there where people were talking about how, this dancing has changed their lives. It may look very simple innovation, but these are people who ordinarily probably will not have opportunity to be able to dance, but now they're able to dance. So this lady said, because of my multiple sclerosis, I had not practiced dancing for 20 years. Great, what a pleasure for me. Sensations, emotions, and music. And the lady said, the feeling of gliding, vaulting can be a way of encouraging adapted practice of dance, and so on. All right, so, okay, that's it. So the true power of robotics lies not in its ability to automate tasks, not just that, but in its capacity to reshape societies, bridge human potential with technology to create a more inclusive, efficient, and innovative. And I'd like to acknowledge my team. I did mention Prof. Eric. Mr. Chibo is here with me, with Daniel, Ms. Kesa, and Ms. Seal. These are all my students. So I'm just going to play a video for you of the dance that we did at CET. specific dance, we didn't do the leader follower. So we actually had someone in the wheelchair from outside. So yes. So
The Wizard of Oz.
yeah. So, but that is at the end of the day. So because of we didn't have time to do the leader follower. But if you saw the episode, that was a leader follower scenario. But in the dance, we didn't have enough time to practice the. So the ideal case would be for the lady who was wheelchair bound to actually lead the other wheelchair and dance with her. So that is the ideal situation. Yeah.
Thanks. Can we just give Prof another round of applause? Okay, now we'll have our next speaker come up.
Use this again. Okay, so just an introduction again. My name is Paul, that's Marcus. Just in question. It took me about 10 years trying to look for a suit. And I couldn't find one. So I do apologize for that. It's easy to find everyone else's picture. Yeah, I never take pictures in suits ever. As you can see, this is okay. So again, brief background about the project, maybe from my perspective this time. So I think we all know a lot of people that are, I don't want to say disabled, but have some sort of disability, right? Yes. We normally jump to one of these options, automatically. By default, it's either we're going to give them a cane or one of those walkers, or just put them straight on a wheelchair. But in some cases, you get people that are unable to use, any of these, which becomes a bit of a problem. Yeah. So, so the research that we're doing was trying to address most of those issues, trying to see how can we assist almost everyone, that has, a problem with, moving around, mobility, basically. Yeah. So until, we stuck with the wheelchair, and then we decided, okay, what can we do on the wheelchair to try and give it most of the abilities for it to assist, almost everyone. So the task was very simple, but, trying to fix that or trying to address that was kind of the difficulty. I think most programmers here will know that all the difficulties involved trying to generalize, a problem, one size fits all. So we took a wheelchair and then, tried thinking, okay, how can we fit sensors? The user needs to be able to have some form of input, The wheelchair needs to be able to move around, yes, and needs to be able to communicate its movements. And at the same time, it should move gently, not just, abruptly, because there are people that are very sensitive to those, crazy movements, right? Yeah. So this was, kind of the general idea behind it. So we just, again, took a wheelchair and then we decided, okay, let's try and play around with what we can do, right? So we just put some wireless sensors, right, and then fitted some software on it. Again, we were trying to find a more general approach. So again, simply put, you want to have a wheelchair where you can attach anything onto it and can still work, right? So depending on the kind of disability that a person should have, what sensors can we add onto it, right? Yeah. So we kind of separated the two to say, okay, how about we leave the controls physically on the wheelchair, right? And then any device that wants to do any form of communication with the wheelchair can then communicate with the wheelchair what it should be doing. So that's how we separated the two. And so, yes, this is just kind of a layout of how we approach the issue. Use an ESP32, for the wireless communication, and then do the remote controlling if you want to do the remote controlling. So any device can then communicate with the device using any form of communication, that you want to communicate with. And this is where the big problem was, because, we try fitting ROS. I think if anyone here has worked with ROS, most of you will know sometimes it's a pain, right? Yeah. You try this version of ROS, it's not compatible with this version of Ubuntu. You try that, it's not compatible with that. But then you have these libraries, they're compatible here, this is not compatible there. So yeah, those are just some of the problems that we had when trying to retrofit the whole version. So again, we ended up just building sort of a container that would then allow you to communicate everything without having to change most of the software, right? Yeah. So if you have, again, someone who's blind and wants to use the wheelchair, technically they can. It's retrofitted with the sensors to allow it to move around within a building without getting into obstacles. Yeah. So any kind of disability can be addressed, with the setup that we did, right? So yes. So we started off with, I think after retrofitting everything, you've seen some of these videos again. So here was after we fitted most of the sensors now and the control of the wheelchair, right? So in terms of the control, I'm controlling it. So the guy okay, let me just. So I'm the one who's controlling it, right? But most people still cannot tell how the control is happening. Right? I will explain in a bit how that is. So you will see again, I'm able to just stand there. And you can think of someone who is unable to move their limbs in any way, right? Yeah, but you can literally just put them on the wheelchair and they can be able to still operate the wheelchair without having to, struggle too much with it, right? Yeah. Again, I'm just standing there, and yes, you may see my hands moving, but the movements are not really related to what the wheelchair is doing. Right? Yeah. Okay, and then yeah. So this is one of the students, Gesa, and Gesa is wheelchair bound. She didn't start off like that. So I tried the whole test with her to see how easy would it be for you to actually drive the wheelchair or move it, Yeah, because I mean, sometimes we as engineers do not take into consideration what, the actual user is going to be doing. So I wanted to get a feel from her. Would it be easy for you to actually move this around? What would you like us to change here and there? What other additions do you think would be helpful for you, to give you a bit more flexibility towards moving the wheelchair, right? Yeah. So again, we wanted her to be part of the vaulting project, the dancing wheelchair, yeah, where she can easily dance on the wheelchair without having to, fiddle around with the joystick. Just enjoy yourself while you're dancing on the wheelchair without having to do any crazy movements. Yeah. So that was the one thing. And then one of the other tests that we did was to try and see. So you'll see there's a camera there. Again, I will show. Yeah, there's a camera mounted on the wheelchair, which is able to basically detect if there's a person in front. So instead of having to push a person behind, the wheelchair, how about the person just follows you behind, or yeah. So you can just basically tell the wheelchair, follow this person. So I was just trying these crazy movements again. You'll see the control is not so good. Why? Because currently we don't have any feedback from the wheels. So it's just let's move, and the wheelchair moves, and then it's like, oh no, I didn't see far, right? So we're not getting any feedback yet. Again, the idea is we want to kind of have sort of an add-on feature. It shouldn't just be, you have to go and recreate an entire wheelchair. You just have to plug something onto the wheelchair, and then you can add features onto it. So for anyone, something that is going to be very easy to create. Right? So again, you'll see, yes, a more struggle here and there, but it's still able to track, what it's seeing or what it's seeing. And yeah. So yeah. Oh yeah. So this is don't mind the wires, please. So this is basically what just an insight of what is happening there. It's just using the Intel wheel sense to get how far you are from the wheelchair, and then which side are you moving, and then the wheelchair has to keep track of that and then make a decision based on that, So if it's following you, it knows I need to follow this particular individual. Yeah. Yeah. Right. Yeah. Okay. So that's just the one side of it, right? Yeah. And then this one again, you can see, but maybe from a different angle, you can see what was actually happening as the dance was happening. So you'll see, so I'm standing there in, this is my everyday outfit. Yes, so I'm the one basically who is instructing. So I'm more of the conductor. Yeah. Again, with the dancing wheelchair, we wanted to have a lot of people, where I can just stand there and conduct the whole show, or anyone can stand there and conduct, the show. Yes, there can be a leader, someone who decides, okay, this is what's going to happen. And then all the wheelchairs communicate with each other and decide, okay, this is what we're doing. So all the dancers know exactly what's happening, all the wheelchairs, bumping into each other, right? Yeah. And then, it never work. Is it this way? Yeah. Okay. So here, this was when we started, adding more wheelchairs. So can we add more wheelchairs? So again, I said with controls, you can basically use almost anything to control the wheelchair, right? So if you want to use your cell phone, you can use a cell phone. If you want to use your watch, you can use your watch. If you want to use a computer, so basically anything that you want to use, right? So if it's any form of sensor, that sensor just communicates with the wheelchair and then basically tell it, yeah. And the wheelchairs can communicate with each other. So again, we're just trying to create this network of wheelchairs that can communicate, hey, you can't use this route because it's flooded or they are doing this, so we need to find a different route. So things like that, right? So they all are able to communicate with each other. So here we just want to see if you have one controller, how quickly can it jump from one to the other at the same time? Yeah. Or same controller, yeah. Can you have one instruction? So this is where we now have this, orchestra or this dance show that we're trying to do. Can you have one conductor, giving one command or just telling everyone, let's do this, then everyone is all dancing in synchrony and the dance is all happening, smoothly, without having to give too much, to the users, right? Yeah. So again, there is still going to be some input from the users who tell the wheelchair, no, I want to move, I do not want to move. Or you can tell the wheelchairs individually, no, you need to move, you need to move, right? Yeah. So the other feature that we got from Kisa, who's our student as well, was she said it's very difficult for her to sometimes, get the wheelchair out of the shower. She has to carry herself, go to the shower, and then she gets in, and then she has to push the wheelchair away. So one of the things that she wanted to is how can I push the wheelchair away, have it go away, and then when I need it back, it can come back again. And maybe late at night when I sleep, it doesn't have to sleep next to me. It can charge, right? And then I can call the wheelchair again. Yeah, it's time for me. I'm waking up now. So here, yeah. So she doesn't need, someone to always be there, to kind of assist her. She has all that help by herself. So yeah, I think that's just that was a brief summary of the work that we're doing with the wheelchair, right? I think that's, yes. And those are just my students currently, who are very hard at work. So I don't touch wires anymore. Yeah. So they are the guys who are doing all the touching of the wires, and I'm that guy. Yeah. So yeah. I'll take any questions. 10 questions. Yes, sir.
Yes, I have a few. The first question would be, is there an override between the joystick and the communication with the cell phone? Let's say I'm tired of gestures. I want to control it manually. Is there an override?
Yes, there is an override. So there's the person sitting on the wheelchair is the one who decides whether it's being controlled by external or they can decide which direction they want to control. So for example, if they're following someone, the wheelchair can take over the distance between and then they take over the direction. Or the wheelchair can take over both, the distance and the moving around, or they can decide whether they want to keep, controlling the forward, backward motion, and then the wheelchair will handle that. Yeah, so it's just optional. But the person sitting is the one who decides. Yeah, they have priority. You don't want to be moving and then you don't want to move. So, yeah.
The other one it's just probably it's out of context, but you were using your hand. You were using your.
No, I wasn't.
You were using your watch.
I wasn't.
Because you were doing this and it was following what you were doing.
Well, if you go
Or
back,
it was not you in the wood.
if you go back again,
Yeah, they.
they say a magician never reveals their. If you go back, you will see I was not. A lot of people tend to think. At some point, I almost undressed fully. And someone was like, "No, you're using your watch." I was like, "Okay, here's my watch." They were like, "Oh, you have a sensor on you." Then I'm like, "Okay, jacket off." Okay, maybe it's in. You know what? Let me just take off everything. So, you will see, I think, in that video there, yes, you see my hand is moving, but which hand is moving? I don't wear my watch on this hand, it's on this hand. But you could say maybe I had it on that hand, right? Yeah. But if you look at the movements, they're not corresponding to what the wheelchair is moving. And at some point you will see my hand will go down, but the wheelchair will continue moving. Yeah.
Oh, I get it.
No, but you see now it's still moving. My hand is in my pocket. You want to see my other hand?
No. Now I understand now. Now I understand. I got the secret.
Yes, so that's yeah, that's part of it. So you can have any form of input from the user in any form of way. Yeah, as long as they can move their eyes, you can use that as an input to the wheelchair. So, like I said, we're just trying to generalize the whole wheelchair in such a way that you basically just create all the external parts that you need to control the wheelchair. Yes, ma'am.
Oftentimes, if someone's like a high-level quad, I heard you say that you can use their eyes, etc. Have you thought about the fact that, if there's any trunk control that can use the trunk or almost like an intent, either force control or some type of tactile control or body control through the seat? They decide if they want to go left versus right using their trunk?
Okay, yes and no, right? So the yes part is because, like I said, it's more of a general type, where if you want to use any form of input, you design it for that. So from now, it's basically just designing all the external controls that can be applied onto the wheelchair. So if you want to add force onto the seats, you can put your force sensors in the right place, and then you just have to do your correct calibration, and then you just teach the wheelchair or teach the person now to see, okay, can you move with, you're able to move in that, however you want to move, and then the wheelchair will then respond accordingly.
A follow-up question about dancing. So I thought I really loved that presentation about the vaulting. Can the user, if they don't have much control, or you've given them some control, can they pre-program a dance that they want to do with their wheelchair, and then the wheelchair performs it with them, in that sense? Or is it like a desired trajectory that they can give to the wheelchair? Can they program the wheelchair themselves?
Okay, so I think one of the things that we wanted to do was to have, like I said, a main control station is going to be handled. So in the case whereby you wanted a group of wheelchairs together, so that whole show needs to be directed there, and then that computer will then send all the commands to the wheelchairs. You need to be here, you need to be there. So it doesn't necessarily have to come from the one wheelchair only, but it can come from one point. You can control as many wheelchairs as you want to. So because you can use any form of communication, well, not any, but so it's either MQTT or in ROS or any of those, right? So you can program your dance and then send your dance through and say, this is the dance. So these are all my individual people, and this is what they all be doing throughout the dance.
If I could just add to that, the vaulting wheelchair actually is different from the normal wheelchair. Okay. So this normal wheelchair is the one that we use just to control dance, but then the vaulting wheelchair was actually mechanically made for dancing. So you actually use your upper body. So as you move your upper body, you're able to move in different directions, and then the wheelchair actually flows with you like that. So I didn't have the time to show the video for the. So there are specific movements that you can do with the vaulting wheelchair that you cannot achieve with this normal wheelchair.
Yes.
It's a quick question. So is kind of the idea going to be that once you kind of like it's finished like the first version of this, you're going to upload the Docker like open source so that anyone can kind of install that, so long as they kind of install the correct sensors on the wheelchair according to the specification you give, you'll be able to like smoothly use this. Because like you said, right, like the whole thing with Rust and all of that is that you have issues on the Rust versions, you have issues on the Ubuntu version, issues on the libraries. So after you have gone through all of the hard work of like creating the Docker environment of that, I did to open source it.
How much? Okay, I think that's one thing that we will need to discuss. Yeah, because there are some parts I think that Prof said we need to go in first, and then we'll see what are we distributing out, to the public. Yes, there are going to be some things that we say these are for public. Then there are those things that we say these are only for because we are trying to commercialize some of the stuff within the wheelchair as well. Yeah, some of the outcomes that we have. Yes, I don't know if Prof you want to add.
Yeah, no, you're quite right. Because most times we do research, we don't look at the commercialization. So we happen to meet the minister sometimes beginning of the year, and he told us we need to commercialize this. So we're actually looking at in that direction too. So we don't want to be open source yet. Open source is going to come later.
I have more questions. Anyone? It's going twice. Okay.
So we're just going to take a quick water break, and then we'll come back for the field robotics talk.
We're doing good. Just so that the Google Scholar. There's always that scary point where the current year sees previous year. You make put the controller on our chest.
Basically, it's actually
Basically a wheelchair.
same time we need to move between the media and the
It's like a little motor on the top.
Exactly.
names are top.
Sounds like a good
So he said that something came up, and so he said part two.
Hanson just wants to
I think what he's going to do is he's going to put that on the poster session he came.
Prof just wants to take a group photo probably because she has to go in there now.
I don't think that, I mean, I don't know if it's useful now to check the audience.
Check the audio.
Yeah. Interesting.
Okay. So for our next session, we're going to have Dr. Stephen James, who is a senior lecturer at ethics and is also a deputy director of Real Lab. He also moonlights as tech support for last-minute robotic conferences. But yeah, he's going to be talking about one of the very interesting projects happening at Real Lab.
Well, thanks, Jen. Okay, so I realize I'm the person standing in the way of lunch, so hopefully it won't take too long to get through what I want to talk about. I'm very aware of that. As Jen mentioned, this is the field robotics session, and so for those who do know me, you'll find that very ironic that I'm the one presenting the field robotics session. The only thing whiter than my skin are my shoes, and that's just an indication of I don't like to go outside. But there are some interesting problems outside, and so occasionally we do have to go out and do some stuff. But my focus is really on autonomous field robotics, so then I can stay inside, the robots can go outside, and I don't have to mess up my shoes. So kind of that's my motivation for everything. And before I jump into the presentation itself, I added a slide this morning. We had a very interesting talk from Professor Mutumbara, and at times it was a bit oddly antagonistic towards it, so I just want to clarify that we do publish stuff here. I'm fairly junior, so I haven't published a book that costs $157 for the ebook version, but I have written some stuff, and like we do have the internet, and so you can go onto the internet and you can get my book on Intro to Algorithms and Programming for the price that I think my students should pay for textbooks, which is $0.00, which if you do the conversion is also 0 rand. So there's that at least. Anyways, so Elisha kind of killed me because if you were here for the opening session, hopefully you would have heard the talk from George Conadaris, and he spoke a lot about kind of the early history of robotics in South Africa, and kind of he started from the 1980s, and I thought, oh, that's a good way. I'll do that. I'll go a bit further back. And then we just heard a whole history of robotics. So he's really like crushed my slide here a bit. And maybe what I thought I'll go slightly further back than that. So just a quick brief history of robotics, slightly further back. So 4.6 billion years ago, and it was not a great place to be, and it was quite hot. I don't know what the temperature was, but it was at least 30 degrees, potentially more. So you didn't want to be around without aircon, and so not a good time. And then some stuff happened, which was cool. And actually, South Africa is a very interesting place when it comes to like early history and humanity and all of that, and we'll get into that in a bit. One thing that I thought was just fun to mention, which maybe, well, I certainly didn't know. Maybe people in this audience are more knowledgeable than me, but maybe not. So I thought I would share this. We've all heard of like this massive meteor that like hit the Earth and then killed all the dinosaurs. And it's like, you know, there's this massive crater in Mexico, et cetera, et cetera. But did you actually know that like there's a crater called the Vredefort crater, which is right here. And this is the largest meteorite impact to ever impact Earth. This was like 2 billion years ago. This happened. The crater itself is something like 200 kilometers in radius. So really big, massive impact. And so that's something that South Africa has, which I think is cool. And actually that's where all our platinum comes from that impact. So I didn't know that, but then kind of I was researching history and I found that. So I thought that was cool. Okay, so Earth 4.6 billion years ago, massive crater impact 2 billion years ago. And then a couple years later, in 1924, a town called Taung in the northwest. You guys may have heard of this place. In 1924, a bunch of quarry workers stumble upon some bones and a skull in particular. They call their line manager of the company that runs the quarry, comes over, they say, look what we found. He takes it, he gives the skull to his son. Son places it on the mantelpiece above the fireplace. And a while later, a student, Josephine, visits the son, and she sees the skull, and fortunately, she is an anatomist at Wits. She's doing a PhD there. And she calls a professor from Wits, Raymond Dart, to say, I've seen the skull, and it looks a bit like kind of your early monkey-like species that you've been studying. Do you want to come take a look? And so he goes over and he takes a look. And this is actually the first discovery, essentially, of a species called Australopithecus africanus. So this was in 1924 in the Northwest Province. Australopithecus means like southern ape, and then Africanus, self-explanatory. And while this is a massive deal, right, this is not like the oldest hominid or anything like that. You can see it's like 3.3 to 2.1 million years ago. Very old, but not the oldest. If you're from Ethiopia, or if you follow this kind of stuff, we've got like Lucy. Lucy is much older. You can see like between 3.9 and 3 million years. So this species here is Australopithecus afarensis from Ethiopia. And these were discovered kind of in the 1970s and so on and so forth. But what's interesting and why this is so important, Australopithecus africanus, is because of the intactness of the skull. Like prior to this, these are the kinds of things you might find if you go and you make a big fossil discovery. You've got like tiny bone fragments, and people do a lot of work to kind of piece them together and work out exactly what fragment this belonged to, and so on and so forth. So to discover like an entire skull of an early hominid was like a massive find, like a huge deal. And this was called the Taung Child. And they reckon maybe like 3.5 years old when it died. Okay, so that happened. And then a bit later, in 1936, in the middle of nowhere, literally I went on Google Maps and it's just this. It's very dusty and you don't wear white shoes there, so it's fun. A guy a paleontologist from Wits, Robert Broom, makes a discovery which he calls TM1511. So nice name there. And it's kind of this partial skull over here. And it turns out that this skull is also belongs to Australopithecus africanus. Okay. Then in 1947, another skull is found in the exact same middle of nowhere, again by Robert Broom, and one of his co-workers, John Robinson. They find the skull, and the skull is actually housed here at Wits, and we might see it later on tonight. This is called Mrs. Pless, so if you've heard of her, it's actually a he, turns out. But it was 1947, they couldn't quite tell. You can see there's like a big hole in the skull. That's because Robert Broom's preferred method for excavation was dynamite. So we don't really do it like that anymore, but he was just like, let's blow some stuff up and see what we get. So that's why it's missing a piece of skull. But this was even more important than the Taung Child, because this is the same species, but this is now a fully formed adult. And so that tells you a lot more about the development of Australopithecus, the dentures, all the rest of that. Okay. And then fast forward a few years to 1997, a researcher, Ron Clark, and workers make a discovery. And this discovery is kind of the largest intact skeleton ever discovered of any of these kind of early hominids. This is called Littlefoot. This is the skull over here, and this is like an arm, and it's kind of embedded in the rock matrix. It's called Littlefoot because the first parts that they find are like the ankle and the bones of the skeleton. And over the course of 20 years, they dig it out. So it took 20 years to like extract this thing from the rock. And then this is like the biggest thing that's ever been found because it's like a full, complete skeleton of one of these early hominids. And you can actually see it at Wits. I think Benji's been down and seen it in the glass case. This is the kind of thing that it looks like, a full skeleton. So very important, most complete skeleton ever found. Okay, And then some marketers got hold of things and like, well, this seems very important. Let's give it a cool name. And so they call it the cradle of humankind, which is, arguably like the best name you could have ever called it. Very, evocative. And, if you're claiming something, you might as well go all the way. So we call this area the cradle of humankind. This area in total is something like 47,000 hectares. Which I don't know how big that is, but it sounds pretty big. It contains a bunch of things like the Sterkfontein caves. Those are where those previous fossils were found, and that's owned by the University of Wits. It also contains a bunch of other caves, so like the Rising Star Cave, if you've been following more recently, Homo naledi and things like that. The Rising Star Cave is not too far in the same area as Sterkfontein Caves. There's also like Australopithecus sediba, which is also in another cave not too far from here. So that entire area is just a hotbed of fossils that can be found, early hominids and things like that. And one reason for that probably is because there's nothing going on there at all, so nothing has disturbed it because you don't want to live there. It's horrible. Okay. So let's talk specifically about the Sterkfontein Caves, because that's what we're interested in today. So Sterkfontein Caves, it's hard to get a kind of impression of the size of the caves because the rock formations are quite weird and things like that, but it's rather big. In particular, the tunnels that we know about are total more than 5 kilometers long, a very big cave. There's a lake, and that lake leads to an underwater area, which is also another 5 kilometers long at least. So far, since, for the last 70, 80 years, for the times they've been doing research in these caves, they've mapped probably about 20% of the entire cave, just the dry part, nothing underwater. And one of the things about the cave, and we'll see examples of this later, is that not only are we able to find fossils that shed light on early hominids, but it also tells us a lot about the ecology of the area at the time. So, there's millions of years ago, it tells us what did the land look like, what kinds of animals were around, what was the vegetation, things like that. And that's also important for understanding, Australopithecus is interesting because it was around the time that the stone tools were starting to be created. And so that kind of starts to paint a picture and a narrative of what's going on, what animals are there, is this what's causing, various tools to be developed and so on and so forth. So it kind of all fits together to create this picture of what was happening 3 million years ago. Another fun fact that I didn't mention, and also a fun fact about the formation of Earth, is that there's like a hypothetical supercontinent before Pangaea called Volbara, and half of that is supposedly in this area. Half of it is in Australia, but we don't like them, so it doesn't matter. And whether or not you believe that existed before Pangaea, the interesting thing is like some of the rocks here are like the oldest rocks on Earth, because we know that there's land, and then the land gets subsumed and the lava, and then the magma comes up and creates new land. So the Earth is like constantly in rotation of ground. Some of the rocks here are, you walk down and they'll be like, oh, this rock here, 2 billion years old. So that's cool, I think. Even though it looks the same as every other rock, but 2 billion years old. So that's cool. Okay. So some of the things you can find at the caves and shed light on the history of humanity are these things called microfauna, and these are very abundant. So these are like the bones of shrew and field mice and things like that lived millions and millions of years ago, that kind of have just accumulated in this cave. They've died, bones have fallen into the cave, and they've just sat there. And they're kind of, so abundant so that like if you pick up some dirt from the ground, you'll just be holding bones. So plenty of that to go around. And that tells us something interesting about the kind of fauna that was going on at the time. And then more interesting are like when we discover things about like carnivores. Carnivores are much more rare than kind of the field mice and things like that. And again, that gives us a sense of what's the ecology, what's going on at the time. Were we hunters? Were we being hunted? Is that why certain tools were developed and so on and so forth? Yeah. The cave itself is also very important from a geological perspective in terms of understanding how things change. So obviously 3 million years is a long time for things to move and mudslides to happen. And all of the sediment tells us something about what did Earth look like at this point X million years ago. I have been told some stuff about this, but I can't remember. I'm sorry, I don't. Geology is not super exciting to me, so it's important, though, don't worry. And then also what's interesting is like the morphology of the cave. So it's a bit hard to see, but like this is the cave and this is the ceiling, and you can see like there's a tiny, tiny hole at the top. And this is one of the reasons why fossils are so abundant and why this cave is so important, is because essentially this cave sits obviously below the ground. The ground is just regular felt with these holes. And so what would happen is animals and early hominids would just fall down these holes and die. And the cave was inaccessible. The cave only became accessible due to mining activities. So they would just fall down and die and remain there for the next 3, 4, 5 million years, whatever the case. And so that's why kind of so many fossils appear in Sterkfontein, because of its structure. And one interesting thing, again, that we don't really have a sense of is how do we kind of work out where we are in the cave relative to the surface, and, you know, kind of work out where these holes are, and, you know, does that tell us something interesting about the world? Okay, so there's a lot of opportunities in the caves. One of them, and the main one, is because, as I mentioned, only 20% of the caves have been mapped, and that's just the ground. And so here's kind of a map that has been built of like different LiDAR points over the years, all put together. What you'll also see is interesting is like the entrance to the cave is here. Again, like this is not a natural entrance. This entrance was created due to mining activity back in the early 20th century. So we blew a hole and then we created an entrance into the cave, and they went in and they mined dolomite and all the rest of that. But here's the entrance, and here is Littlefoot right there. So if you do visit the cave, so if you have visited before, you walk in the entrance, you walk down the stairs, you turn right, and that's where they found Littlefoot. So a lot of the big finds are within something like 30 meters of the cave entrance. The cave is 5 kilometers long. You can imagine there's lots else out there. We just don't know about it. It's very hard to explore. Okay, cool. Okay, so this is kind of all of the context for the project that we're currently working on and that I want to tell you about today. Okay, so we have a project with a bunch of collaborators. The project is called the CAVE, Robotics for Assisted Discovery and Landscape Exploration. I will take credit for that acronym because it's Cradle. I think I'm supposed to say something like, we are not affiliated and the views expressed by us do not reflect on the National Society, blah, 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 but we are funding from them. I think I can say that. So we are funding from National Geographic to run this project of deploying robots into the caves to do assisted discovery and landscape exploration, which I'll talk more about. And we also have a bunch of collaborators. So maybe the most important one is Dominic Strafford. Dominic is a professor here at Wits in the School of Geology and Archaeology. And he is the cave director. So the cave is his domain. He's kind of drives the research agenda there. So we're working with them. We've also got Richard and Harong from the computer science department, doing a lot of like the computer vision stuff. George, who hopefully you all saw at the beginning, giving his presentation. George at Brown. We've got Jeff Hollinger at Oregon State University, who does a lot of like underwater robotics. And so we're working with him on things. We've also got James Tompkins at Brown University, also doing kind of vision stuff. And then Nick Hawes and others at Oxford, and I couldn't fit them on the screen, and it doesn't matter. Also doing kind of working with them to do kind of robotics in these difficult environments. Okay, so what we basically want to do is say, let's go in, let's use robots and a variety of robots to map and understand the cave structure and build this map. And then hopefully that leads to kind of new discoveries that we can make along the way. And that we couldn't make just with, you know, human labor. Human labor is very hard. As I mentioned, it took 20 years to just excavate the thing once you found it. And so it's painstakingly slow. Like, I don't know if anyone has done anthropology and been on a field trip and had to kind of, you know, do a dig, and you sit there for 6 hours brushing away dirt to try and get at like some stone or something. It's backbreaking work. And so kind of anything we can do to make that better and to accelerate research in that direction, that's what we're after. Okay. So how are we going to do this? Well, the obvious thing to do is what we want is a massive map of the cave system. And in particular, we want a 3D map. So we want to go in there, collect a bunch of data, build a 3D map, and then that's it. Easy peasy. And what we want to do with that map, fundamentally, there's many use cases for it, but the main one that we want to do is we're going to use the map and use known geological and morphological features that, that geologists and anthropologists and paleontologists all know about and all know are reasons for why fossils would be in a particular place. I'm going to use that with machine learning to build a predictive model to say, here's my map of the caves, and here are kind of hotspots or areas of interest that you might want to check out. And we can then use that to kind of guide exploration to say, okay, well, let's go investigate this area, let's go investigate that area, and so on and so forth. And this also has other downstream applications, so things that I'm excited about also like science communication. Imagine if you built a 3D model of these caves, great, you can like make a website and people can go and visit virtually, or you can do like a virtual reality tour and things like that. And you can kind of drop points of interest and people can go up and say, oh, this is where Littlefoot was found, and get more information. So I'm excited also about the kind of the science communication aspect of things. Okay, but building the cave, one of the important things is this is not just like regular 3D mapping of like a building. Like you're a robot and you're trying not to crash into things so you can deliver the coffee to the person. We do that a lot. This is a picture of the caves. It doesn't come out as now. The actual image that we took here was like 100 megs, so I didn't put that in. I put like the JPEG in, so it's not some quality. But like this is what the cave wall looks like. And one thing that's important for us to capture is not just like, oh, there's an obstacle, this is the shape of the cave wall. What we need is the texture. We need the texture because I said like we're going to build this predictive map based on geological features. So we need to know, we need to capture, we need to have information in our map that says, oh, this kind of rock here is different from this, and there's this line running down, and all of that is important. In normal SLAM and normal mapping and all of that, you don't care. You just care like, oh, there's an obstacle and I can't go here, and it juts out a bit because the robot doesn't want to collide. Or maybe you have like some very coarse grained thing. Here we need very fine grained detail because all of this information is important. So I've been told by geologists. Again, I don't know anything, but I've told like this is important for some reason. So we need to capture that in our map. Okay. So let me just go back. Cool. So this is kind of the team that we're currently working with. Right. So a lot of them are actually in this room. So here we are at the caves one day, including myself, and I'm very unhappy because it's outdoors and it's hot. And we brought along some of our robots. So you may have seen this yesterday, the Husky, whose battery wasn't charged, and the Unitree, whose battery also wasn't charged. And then there's just a nice dramatic picture there in front of the caves. And here's us getting a kind of pep talk from Dominic, just again about the history of the caves and things like that and the importance. So this is us at the caves. Again, these are just kind of an assortment of videos of us. This first one is just us driving to the, we weren't going to carry the robot and it's supposed to drive everywhere, so we just drove it all the way through the bush to get to the actual cave area. And then kind of we had this deployment of the Spot and the Husky, not Spot, sorry, the Spot is too expensive. And the Husky in the caves. I think Helen mentioned don't use the quadruped in the mines. The caves are slightly worse than the mines. It did okay, actually. It did better than I thought it would do. Obviously, this area is like the public area where it's quite flat and things like that. It did do better, and then it broke also at some point. But that's okay. That's what robotics is about. This was kind of the first, I suppose, deployment of a robot in the Sterkfontein caves, which is, I suppose, something. And then we've got our Husky, which is much better and actually went up extremely steep areas that I didn't think it was. I was a bit worried it was going to like flip back over, but it actually did very well. I did have to like stand behind it in case, and then on reflection, I was like, I probably shouldn't stand behind it because it's going to crush me. But I can heal, and this is very expensive. And things like that. So this was just kind of our robots in the cave. And there's a whole bunch of challenges. Obviously, the first thing is we want to go off and collect data to build our map. And that's great. There's a bunch of challenges. One is the cave is very big. As I said, 5 kilometers and also like 30 feet in the air kind of thing. Cave is really big. And so collecting data is really hard in a big space because it's going to take a lot of time. Also, cave is very dangerous. So it's really hard to see the perspective. But like, I think it's Benji's shoe. and this is instant death down here. And he's like, yeah, this is not open to the public, this part. So we're like sending children to their deaths. But and Dominic was like, yeah, just jump over here. Just jump. Like, okay, sure. Sounds good. That's why I don't go outdoors. It's very dangerous. Then there's also kind of like these weird areas that are like inaccessible, basically. Like, you know, you want to get into this like mini cavern over here, but if you had like, first of all, okay, so if you had like a quadruped, you're not going to get down there. If you have a husky, maybe you can get down there, but you can't get back up. But obviously you could get a drone in here, but like, could you get a drone to this in the first place? Maybe not. So maybe you need like a drone on a wheeled robot, and you launch the drone from there, and then you fly in and come back out, and these kinds of things. So a whole bunch of challenges there. And not only is the cave very big, it's also very small, and contains areas that no normal person should ever venture into, lest you appear on a YouTube video of caving disasters. So we want to go in there. Well, humans shouldn't go in there, but robots should go in there and then hopefully come back out. Okay. So, and also there's a lake, which I haven't showed you yet, but as I mentioned, there's a lake. So we're taking like the Avatar approach. The water, the earth, and the air. There's no use for fire that I found just yet, but if anything, please let me know, because that would really complete the set. So let's talk quickly about water. This is what if you Google like lake in Sterkfontein Caves, you get something that looks like this. Very pretty. I don't know, the lighting that they had was, I don't know what's going on there, because this is what the lake actually looks like. Let's play this video for you. It's not pretty. It looks like this. Like, I know it doesn't quite reflect on the projector, but this is actually how dark and scary it is. Not like this. This is like Bahamas over here. So that's great. I encourage you also to never watch this video on YouTube about the Sterkfontein Cave tragedy, where a bunch of divers went in 1984, and then one didn't come out. And if there's anything I can tell you, it's don't watch this video, and then also, if you insist on watching this video, don't do what I do, which is watch this video at 11 o'clock at night and then try to sleep afterwards. Long story short, a bunch of divers go into the cave. They're busy mapping it, things like that. One guy decides, no, it's a good idea for him to go explore down like a tunnel here. He goes off. He leaves the guide wire. His friends don't notice he's gone off. They get out. They're like, where's the dude? He's gotten lost in this cave underwater, and he has limited oxygen. He like finds an area that's like a pocket that, you know, he can get out of the water, sit down. It's got air and things like that. And then he has to kind of make a decision because he doesn't know where he is. Like, does he get back in the water and try and make it out? Or does he sit there and does he wait for someone to come get him? And he decides to sit there, and a week goes by, and 2 weeks go by, and 3 weeks go by, and he's sitting in the dark, and his battery's died, and now he's too weak to actually, you know, make it out. And eventually they find him after like 6 weeks, but he died like the previous week. So horrifying. The reason I'm telling you this is not to dampen the mood, but just to say that after this incident, no one is allowed in the lake. So humans are not allowed to go in the lake anymore for obvious reasons. And so if you want to explore the lake, there's only one option, which is to do robotics. Okay. And so kind of the idea here would be, how do we do exploration underwater and also build a 3D map underwater? A very cutting edge thing. How do you build a 3D map underwater though? But first of all, obviously going underwater, collecting the data. We don't know at all what the structure underwater looks like. There's obviously no light and no GPS, that goes without saying. Any motors that you have on your, this is our like Blue ROV 2 kind of thing. Any motors or propellers will kick up silt, so that will obviously just cloud the entire water and you won't be able to see anything. And also if you lose the robot, then you can't get it back, so it's done. You can't send anyone in to get it. And so we're working on kind of with Jeff over here on using sonar to do this, and they've got a project currently going on of doing this exact thing, but like in a quarry where it's quite safe. Then once they're finished with that, we will kind of deploy in the caves and go from there. Okay. Enough about water, which is very scary. This is less scary. So in terms of air, obviously the thing that you have to use here are drones. The areas are like 30 meters plus high, obviously very highly irregular and things like that, and obviously no GPS. And so the story we were told when we first visited the caves was someone had come with a drone, like a DJI drone, and they're like, we're going to get some data, some LiDAR data and whatever. And then they quickly realized that they needed GPS to kind of do their thing and do obstacle avoidance and hover and things like that. but their drone was very expensive, so they didn't want to do that. So what they ended up doing was they just took the drone and they held it in the air and then they walked around with it. And so that was the last time someone tried a drone. So we have kind of LiDAR data, point cloud data to maybe like 7 or 8 meters. That's about it. So kind of the obvious thing to do here is to deploy drones in the space. And even one of the speakers yesterday, was talking about these kinds of things. Like this is the Dronut, I think, which is a cool name. It's like a little small thing. The propellers aren't exposed and so won't smash themselves on the rocks and things like that. And so kind of either buying or building custom ones with cages and things like that is the way to go here. Cool. And the drones actually are not kind of the problem. That's like the easiest area probably to collect once you have the right things. We're also kind of doing some research here. So this is one of our students, Tevlin, and he's looking at if you want to do kind of dynamic fast obstacle avoidance, things like that, and you have various quality sensors. So maybe you have like low quality LiDAR, high quality video camera or whatever, and you're moving at a certain speed and taking actions at a certain frequency. What's the effect of that on kind of obstacle avoidance when you're navigating through these areas in like the RL setting? So this is kind of just a simulated environment. Obviously, we won't be using a quadcopter, but just for simulation purposes, he's looking at kind of the effect of sensors on obstacle avoidance and things like that. Okay. The main kind of meaty stuff here is about how do you collect this data on the ground with ground robots, things like that. And so there's a whole bunch of sub questions that we're interested in answering as like a first phase of this. The one is like, how do you remain stable and don't fall over? And then let's say you can remain stable and not fall over. Like, how do you navigate in a safe way? Not like, oh, everything's fine and I can navigate the rocky stuff. And then I just fall off a cliff and now my robot's dead. So that's all about like, how do we move around? And then there's a couple other issues. One is like, how do we ensure, let's say we're going around and taking images of the cave walls. How do we ensure that this is like high quality data? Because we've seen the lighting is terrible and things like that. So how do we ensure high quality data? And then a problem that's really close to my heart, because again, it's also like an hour away and it's an hour back in traffic, is like, let's say we go out and we spend all day there and it's hot and I'm dusty. And I just want to go home and we've collected some data. How do we know we have enough data? I want to come back again and collect some more data. So is there like some way to do this? And this is like, again, very close to my heart. And again, this is, on these two platforms to start off with, and then kind of we're looking at other ones as well. But how do we do this kind of thing with these platforms that we have currently? Okay. So in terms of stability, this is kind of, work that's been done by other people. And the idea here is to say, okay, well, let's take in kind of proprioception data, like, joint angles and things like that, as well as things that are coming from externally. So like RGB, LiDAR, things like that. And what they do is they kind of use machine learning. These are like neural networks over here. And they learn a representation of the features of the terrain. So the proprioception data tells you about the current, like your current terrain where you're standing right now. And the camera and things like that tells you of like what's coming up in the future. And these are just learned features done in a supervised learning setting. And then you can do something like reinforcement learning and you can condition a policy, which is just like a controller if you don't do RL. And you can condition your controller on these representations of your terrain and you can learn how to act to do things like walking. And they do this like actually on the robot itself. So this is like learning directly on the robot, not in simulation. And so you get things that look like this, which is quite impressive. This is also a Unitree, I think. So pretty impressive stuff that they're able to do. Obviously very difficult terrain. And you can do kinds of things like this. Cool. Eventually we'll make it. Okay, it made it, props. And then hopefully you've all chatted to Ibrahim. He was at the poster session yesterday and he's sitting right there. And so his work is, that's great and everything, but the problem is like, if you now have a different robot, then you're gonna have to train all of this from scratch. And so can we decouple some of the parts? And in particular, what we can do is like, we can have like a terrain estimator over here. And kind of this terrain estimator will estimate your proprioception which will feed back into this thing that you've already learned for the robot that you have. And then you learn a policy. So very similar, you just have this extra part here. But what this allows you to do is kind of reuse certain components if you have a new robot. So if you have like a Unitree, you learn all of this. And then if you go off and you get an animal or something like that, then you can just kind of relearn this stuff, but this stuff over here can stay the same. These kinds of things. So you can kind of plug and play these things. You don't have to learn everything from scratch. And so we're kind of looking at this in a simulated environment for now. And so this, I think, is in RACEM and things like that. So, and this is, the Unitree walking in RACEM over here on uneven terrain and all of that. Okay, but let's not worry about that because that's, kind of low-level stuff. Let's just say we've got a very stable platform like a Husky or something like that, and you want to do kind of safe navigation. And so again, this means like, I'm fine like moving around, but I don't want to fall down a hole or fall into the lake or something like that. And so what previous approaches have done is, this is from JPL, I think, at NASA. What they've done is kind of they've used different sensors to build different maps. So they'll have a map of like an elevation map, a full occupancy map, the slope, like a measurement of slope and things like that. And then they basically take all of this and they combine it into one like risk map down here. And then kind of they use that and they say, oh, let's do planning, but plan using this, and then you obviously have costs that are associated with high risk areas and all of that, and you build a plan out that way. And so what one of our students, Gavin, is looking at is, this is great, but kind of you're restricted to whatever you've plugged in here. Like you're just assuming that, oh, okay, the things you care about are like elevation and obstacles and slope and things like that. But maybe there are other things that you haven't thought about, and kind of you're restricted based on what you've put down here. And so what we're looking to do is instead of doing all of that, say, okay, I've got all of this input. Can I learn from data what areas are safe and what are not? And we're going to train something called a point conv. And a point conv is just a neural network that takes in data and it outputs for each pixel on like an RGB image, some value, and that value is how safe or how unsafe that single pixel is. And it does this for all pixels. And so the idea here is to kind of train an agent in RL. You train it and you get a bunch of data that tells you like, oh, well, this trajectory was unsafe because I died at the end, and this trajectory was not unsafe because I reached my goal and all of that. And that gives us a data set, and we can use supervised learning to kind of train this point conv to predict risk and all of that. And so kind of we're working on that there. And then the two other problems, one is how do we get like quality images? So the cave is very dark. You can see kind of how dark it is. Like if there is no light, then it's just black. And we put like a little light on here, and then the light broke. Sorry, Ibram. And so even like putting a light on is not really a feasible thing. So what you want is like good lighting. And so the main public areas have lots of lighting that's been established. But obviously, as you move away, there is no lighting because who's going to install lighting in areas that humans don't go? So one thing we could do is we could just walk around with portable lights, and that's laborious. And also that means areas that humans can't access, we just can't map. So that's not a great idea. And so what Ali is working on over here, and you can talk to about that, is kind of a multi-agent coordination project. And so what you can think about in the setting is like, imagine your Husky is going around and it's going to drive around and collect pictures of cave walls and things like that. What we want is like some drones that are in support of the Husky. And so the drones will come along, and there's no communication down there because there's no signal, there's no nothing, no MTN. And so they have to be completely independent. But what they want, well, what we want is for the drones to learn to position themselves in a way with their light so that when the Husky takes a photo, that photo is of highest quality as possible. And so you could imagine this in a reinforcement learning setting where you say, okay, my drones move to some locations, the Husky takes a photo, you look at that photo, you compute like the peak signal to noise ratio or something like that, some measure of like how high quality that image is, and then you use that as a signal for your reinforcement learning system to train the drones that you have to accompany the Husky to be better and position themselves better to get the best shot possible. So I'm excited about this again because I don't want to carry lights around. It's very hard and tiring. Okay, and then last project that I maybe quickly want to touch on here is David, who's at the back over there, and hopefully also saw him at the poster session yesterday. And this is the idea of saying, let's say down the line, we want to use our data to build a 3D model with something like Gaussian splatting, which is like a new fancy 3D reconstruction method. How do we know if we have enough data? And so what he's looking at is something called view pathing, which, you know, in this case here, it's like a drone flies around and computes like, what path should I take? And can I compute like the information gain of looking at each pixel and what pixels do I not have enough information of? And it uses this to kind of determine when, you know, things are sufficiently good and when things are not sufficiently good. And so we can use all of that, do view pathing, and then at the very end, extract the keyframes and go home and run our big deep learning on our big GPU. And then hopefully we should have enough information that we don't have to drive back and collect more data. Okay. So all of that is just about collecting the data. And then once we have the data, now we need to put it all together to do reconstruction. And obviously one thing is like, we have all this point cloud data, say from our LiDARs, and we want to put it into one coherent map. And so that's a thing, like point cloud registration is a thing, and that's not a major issue. What we also need to be able to do, and that hasn't been done before, is work out the relationship with the outside world. So we could build a map underground, but where does that fit on the surface? And we don't really have a good sense of that, so we need to also do that. But the problem, and as I mentioned before, what we care about in the cave specifically is like the texture, because that's geologically important. So how do we construct a high quality 3D representation that contains those textures that are important for geologists and will be important for our predictive map? And so what we're going to do here is use NeRFs. NeRFs are neural radiance fields. And so just the one sentence summary of what NeRFs are, if you haven't heard of them. Basically, you give it a bunch of 2D images and it learns an implicit 3D representation. It's just a neural network. And once you've trained it, you can give it as input an XYZ position, an orientation, an array. You say like, I'm standing here, I'm looking here, I want this ray. And it will predict like the pixel that ray would hit in your scene. And then you can kind of use that to build a 3D reconstruction at a particular point. So that's what NeRFs do and what they are. And they're actually quite impressive. I'll just quickly play this. So this is kind of, you know, a 3D reconstruction of a bench taken from photos of that bench. And here's a 3D reconstruction in a 360 view. Like this one is just front facing over here. This is a kind of 360 view of various objects, and it's very nice and it works very well. And there's a lot of like support behind this. And you might say, but you know, these are very small objects in small areas. That's not going to work in a cave. And you know, that's true. There's also work done. This is called scan NeRF, and this is kind of big scale NeRFs, using the same idea, but kind of, you know, patching things together chunk by chunk. And so this is all reconstruction. So you go and you collect data, 2D images, and you can build a 3D representation of the entire world. You can see everything is pretty good. The lighting conditions are not, because you can see like, well, maybe you can't see, but the light is a bit uneven because it can't handle that. But, you know, quite impressive the scale that you can run these NeRFs at. So that's great because we have a big cave, so we need something like that. Okay, but the other problem is that it's in the dark, and everything here is all great. This is nice sunlight. This is great sunlight. Everything is wonderful. How do you do NeRFs in the dark? Well, what people have done before is basically this kind of thing. So what you do is when you capture your data, you don't use regular images. You don't use your PNGs or your JPEGs or whatever. You just take the raw data itself, like the raw sense information. So you shoot in RAW and you train a NeRF on that raw image, and you kind of get performance that looks like this, which is quite impressive. And I'll talk about some limitations of this and what we're working on here, but this is kind of, you know, what they can do. I'll also talk a limitation if you want to do this yourself. One run takes about 1 week on and needs like 48 gigs of VRAM on a GPU. If you want to do that, it's a very slow debugging process. Okay, so, but we need this because it's dark, right? And as we said, like, textures matter. So these are the raw images that we took of caves on one of our visits. They're much more impressive in person when you can zoom in and you like keep zooming in and you think it's like a vector image, and it's not. It's just like 100 meg single image. This is the JPEG because I don't want to explode PowerPoint. And these are kind of what the cave walls look like, and they're very pretty and things like that. And this is work, sorry, I should have mentioned with our student Ayrton, who's not here today. So we want to capture this kind of thing. But it turns out when you do images, like the details really matter. And so if you do any kind of image processing, this is a Bayer filter. And this is kind of the standard sensor on a camera. So your camera takes in light, with its various sensors. And now how do you convert that into like an image that you can see? You run some algorithm based on this filter and you kind of combine everything. And at the end, you get like the image that the human can see. This is a Bayer pattern, which says like, well, this sensor picks up blue things and this one picks up green things and blue and so on and so forth. And there's more green because human eyes, we have more green cones than blue and red. So that's great. And this is what almost all cameras have, except the one that we have, which is a Fuji camera, an X-T3. And Fuji have their own custom pattern, which is called X-Trans. And you can see it has many more green things than the Bayer. And Raw Nerf was trained on the Bayer stuff. So it turns out that when you do this, using this kind of X-Trans pattern in the camera, and this is built into the camera, what you get out at the end is green images, because the thing to do if you're doing supervised learning and you're trying to minimize the loss, the model wants to just minimize the loss on the green channel because there's so much green in here. And so you get out green images at the end. And so like when you're dealing with this kind of stuff, like the low level details of the camera matter immensely. And so here are some results of Raw Nerf that are not green. On the left is kind of a ground truth image of a stalactite. I think it's a ceiling, stalactite. And this is like a test set. So this is a view of a stalactite that the model hasn't seen before. And this is the view that the Nerf predicts. If you said, I'm looking here in this direction and I'm standing up there, predicts this. And so what you can actually see, well, hopefully you can see, is like it's captured a lot of this kind of writing. Like the stalactite has been defaced by the public, and so they've scrawled things on it. And you can see that in the ground truth image here, and it's captured a lot of this. So it looks pretty good. You can see like the background though is not good. Like this background over here is very blurry over here. So it's not great. And it's worse if you kind of do a 3D view of it. You can see it's like, this is fine if it's like a video game or something, but this is not fine for geologists. They'd be like, no, that doesn't tell me anything. It's too blurry, so on and so forth. So it's actually really hard to get these models to work in the dark in these settings. I'll show you some more promising results. This is not Raw Nerf. This is something called Instant NGP, which uses hash encodings and all the rest, and I won't get into that. This is like a cave wall over here. This is the reconstruction of it, and I'll play the video for you. And it's actually pretty good. This is like a depth map that you can also extract from the Raw Nerf, from the Nerf, sorry. So it's actually pretty good. It's just coming out very green again, as you can see, as I mentioned before. But actually, in terms of structure and things like that, it's much better. And then on the stalactite stuff as well, you probably won't be able to see. It's pretty good. It's just completely dark. And it's dark because everything is dark. And so kind of a local optimum thing to do here is just make things very, very dark. And you can see like the depth estimation also is not great over here. So still a lot of challenges there that we're working on, but we're making progress in this space. And here are just kind of like some quantitative results to show that like, things are learning. The peak signal to noise ratio is going up, all of that. But there's still a long way to go before we have usable reconstructions. Okay. So kind of that was a quick run through of our project. I'll just stop with future work, which is to say, this is Ron Clark, and this is Littlefoot over here, and he's looking at Littlefoot and all of that. And as I mentioned, like the discovery was 1997, and the full thing was put on display in 2017. So they did a lot of work to find it, and then 20 years of work to get it out. And that's like a long time. He probably had hair when he started. And so kind of a future work thing that, once everything is done and solid, what we want to do going forward is say, okay, well, can we use robots, right? We don't want to do the Robert Broom thing, which is just blow stuff up. Can we actually use robots with drills to help drill away some of this rock? Because, yeah, some of it is very finicky and you have to be very careful. But a lot of the stuff that they find when they pull it out of the rock matrix, you don't actually have to be that accurate. You just have to make like quite a big cut to get rid of a lot of the stuff. And kind of when you get into the nitty gritty details of things, then sure, you might need a human. But can we use things like robots with, planning techniques to plan on where cuts should be made and so on and so forth. But that's obviously future work once we find our robo-naledi or whatever we're going for. Okay, so that's it for my talk. Thank you for listening to me ramble on about random things. And thanks to the Rail Lab for all the support, because obviously we couldn't have done it without all the great students who work on these various projects. So thanks for listening.
Do you have any sort of calibration that needs to be done for all of these sensors, and like how do you calibrate all of them to work together, sort of thing?
So the answer is yes, we would. At the moment, kind of we're doing individual things. So we're saying like, okay, on the nerve stuff, for instance, we're just going to worry about, let's go take some images, and then we're done, and we'll just focus on that. And then kind of we'll take the Husky and we'll say, let's go collect some LiDAR data, and then we're done. And we'll and kind of when we start putting everything together, then definitely. So for instance, on the nerve stuff, one thing we haven't done yet, but it's on the kind of timeline, is to say, well, we have cameras, but we have the RGB image, but we also attach the LiDAR to the setting. So we have LiDAR data. The normal nerves are just trained with RGB, but we also have LiDAR, so we can use that in our nerve training. But obviously that requires calibration of the LiDAR and the distance between the LiDAR and the camera and all of that, which we haven't done yet. So still early phases, but definitely that will be a major thing going forward.
Yes. I'm curious to know how dimensionally accurate is the reconstructions done by NAF?
In terms of like the actual shape and things like that.
Yeah, and especially compared to say photogrammetric approaches like structure from motion.
So actually, we've used structure from motion as well. The images that we took here, so structure from motion will work well when we collect images on a robot. The images we took here were like essentially manual images. So we had like a tripod and we set it up and we took photos and kind of so on and so forth. So structure from motion actually didn't work there very well at all. And we have found in these settings, the structure from motion, the depth estimation is actually really bad. And I think it's just because like it's very, very dark. Like everything is very dark unless you illuminate it properly and all of that. There has been not our work, but kind of the geologists and things have done a lot of photogrammetry in the past and all of that, and that's worked out very well in terms of the structure of the cave and all of that. I don't know what the resolution is, but like they've been using that, and kind of for their research, that's perfect. But if we want to kind of capture the textures and use that to build a predictive map, we kind of want to go beyond that. So people have done that, and kind of for their uses, it's worked pretty well.
So I wanted to ask my first question was actually similar to me, using cold map.
Yes. Yeah. So yeah, and as I say, in this setting at least, we found that like it's actually a problem.
The second one is the data you collect.
Yeah.
Are they available? Are they
open? So not yet. In part because it sits on like one Dropbox and 3 Google Drives, and everyone like it's not coherent. At some point. What we haven't, like, we've collected data, but kind of we've been playing around with different settings. So like on the camera, for instance, just like, okay, should we collect data with a camera with like the X-trans pattern or the Bayer pattern, and like what should the autofocus on or off and things like that. So once we kind of settle on a final thing, we'll then be able to collect like a massive data set with those settings and make that public. So we do plan to like release a paper that's like a data set and benchmark paper to say, oh, here's an interesting data set. Here's all your current like 3D reconstruction models. This is how well they do. Look, there's a massive gap that needs to be plugged. So absolutely, at some point, there's just a lot of organizing to happen around that. Yes.
Is there any reason that you're almost going for like this very fine detail one as kind of the first pass, or maybe it's just the simplification? Because wouldn't you rather go in and maybe just get a more coarse reconstruction of the general layout and?
Sure. Yeah, so that's a great question. The answer is practical in the sense that like when we started this project, the robots hadn't arrived yet. The thing we could do was like the nerve thing, which was just go in, get images, do nerve things. So we're kind of running a whole bunch of things in parallel, which is like, oh, the nerve thing can happen with or without the robots. And the robots will come in, then we'll be able to collect more wide-ranging data and things like that. As I mentioned, like the photogrammetry stuff and kind of more coarse things, geologists have been doing, again, not to the extent that we could do with robots, so we can definitely help there. But just practically and timeline-wise, we've been doing that on that. Yes.
Last one. What is your sort of estimated timeline for this project?
What did we promise National Geographic? I want to say 2026 October. I think we promised them by 2026 we would have a full map of the cave. a full map of the cave to the extent that like we can collect data. So like the pipeline is there. Like if we had more data, we could just plug it in and build more and more. So that's the idea there. I suppose I should mention that like the National Geographic funding is both for like equipment and also for like PhD funding for this. So if people are interested in spending time in caves or are rock climbers, I was promised that like if we get someone as a PhD student that Dominic, who's the cave director, will teach him how to do rock climbing in caves. So if that appeals to you, yeah, we have positions in this. So, yeah.
Question. So, I believe in other places also they have done things like that. Is it a well-researched area, and what are the unique challenges for this?
Yeah, so they've done it, I think, in Malta. I think there was one in Malta, and they've done it with like, I think the pyramids at Giza, for instance. They're kind of like the pyramids at Giza one is more like a Google Street View photogrammetry kind of thing. So people, the challenge here in terms of the 3D reconstruction is definitely the lighting conditions. So all of them, to any extent, are like pretty well lit things, outdoors but pretty well lit. The scale stuff kind of has been tackled before, but again, good lighting. This is very noisy, very low lighting, so that's the number one thing is that. And kind of the irregular shapes. So again, like if you're outdoors and you're doing like a nerf of a building, it's a pretty straight wall and things like that. Whereas here, like every single detail matters, and that's very hard for like a neural network to optimize. It doesn't want to optimize the low-level details. It wants to get big picture, and then kind of to get it to drop below that is very hard to do. So kind of the darkness and everything, aside from actually collecting the data in the first place, which is always hard. All right. Okay, thanks everyone.
Okay, thanks everyone. We're going to just have a lunch break and then we'll come back for the industry session. Thanks.
Coming through. And then let's call this. This will just be. That's. We go. That should all be good.
Ireti, can you hear us?
Yes, I can hear you. Can you hear me? Can you see me?
Yes, we can see you, and we can hear you. Do you mind sharing your slides?
Sounds good. 1 second.
They project properly.
Let me share screen. Can you see my screen? It's currently blank. Can you see my screen?
Yes. Can you hear us?
Yes, I can hear you.
Yeah, we can see your screen. A simulation first approach to robotic assembly.
Okay, so it's awesome. Thank you.
So I think we're just gonna, we'll start in a few minutes. We're just gonna get the participants back into the venue.
Sounds good. Yeah, just let me know when to start.
Sure, we will do.
Awesome.
Okay, yeah. No, it's because it takes forever. Yeah, because what happens is so I'm not sure.
Okay, thanks guys. I hope you had a good lunch. So we're going to get started with our next session. So our next keynote is Dr. Akinola. He is he's currently working at NVIDIA as a robotics research scientist. And he's based all the way in Washington, US, so it's very, very early for him. So thank you so much for being here to speak to us today. Yeah, thanks everybody.
Hi, everyone. Can you hear me?
Yes, we can.
Okay, so awesome. Yeah, thanks a lot for having me. So hi, my name is Ireti. I'm a senior research scientist at NVIDIA's Seattle Robotics Lab. And today I'm going to be talking about a simulation-first approach to robotic assembly. And I would highlight a number of our efforts towards achieving contact-rich manipulation using a variety of sensory modalities. So before I delve into the details of the talk, I want to provide a quick background on why we are interested in robotic assembly and why we choose to use a simulation-first approach to tackle this problem. Robotic assembly, or assembly in general, is quite ubiquitous. You have that in a lot of different industries, from electronics industry to automotive industry, aerospace, just to name a few. And existing industry solutions are usually highly instrumented, using specialized adapters and fixtures to be able to perform the task. So for example, here you have a special end effector attached to the robot to be able to perform this specific insertion task. So these sort of solutions are not adaptable and are quite expensive, especially for small scale enterprises. So from a research perspective, coming up with adaptable robotic assembly system is quite interesting. We choose to use a simulation-first approach for a number of reasons. So simulation can be a very effective way and scalable way to generate a lot of data for robotics. So as a result, they are well suited for data-hungry algorithms like reinforcement learning. A number of research works in different spaces of robotics have shown that simulation can be a valuable tool for robot learning in ways that policies can actually be used in the real world. For example, here I'm showing a work by a collaborator that is based in Toronto, Canada. And they were able to participate in a competition in Europe without having access to the real hardware. And their approach was to replicate the three-fingered robot in simulation, come up with solutions where the agent can learn to solve the task. In this case, the goal is to get the robot to pick up the block and reorient it to match the goal specification. And once they have the policies trained in SIM, they ship their policies to the organizers in Europe who will be able to deploy the policies on the way robot. So this is an example showing how people can leverage simulation to be able to participate in a global space of robotics without having access to a real hardware. So I will discuss our simulation-first approach to robotic assembly along three themes. So first, I will discuss how we can simulate contact-rich interactions in a very effective way and how we use this simulation to train robots for assembly tasks in the virtual world. Then I will discuss how we can transfer these learned behaviors from sim to the real world and how we use force sensing as a vehicle to enable efficient policy transfer. And in the third and final section, I will discuss how we can simulate visual tactile sensors, which is a type of touch sensor, and how we teach robots to utilize the sense of touch to perform robotic assembly tasks. So these three themes are based on three of our papers, which are available online. You can reference them online. So let's get into the first stage, first part. How can we do contact-rich simulation efficiently, and how do we use that for policy learning. I will discuss 3 key strategies that we use in this work. First, we use sign distance field-based collision detection and contact reduction for simulation, how we design training environments to teach robots, and how we use model field reinforcement learning to train the robot on these tasks. For contact-rich simulation, we consider the nut and bolt fastening task because it is found in about 40% of all assembly operations. Besides, prior to our work, it was impossible to simulate this interaction at real time. So it was an interesting challenge to take on from a research perspective. Why is it interesting? Why is it challenging? If you look at the nut and bolt parts, you will see that there's a level of detail that you find in the threading of the parts. For example, for the M4 nut and bolt, you can have as many as 50,000 elements, so triangle, vertices, and faces, to be able to capture the detail of this part. And this can pose a computational challenge for contact detection, contact normal computation, and non-penetration constraints enforcement. So to tackle this problem, our first key insight is to, rather than represent these parts as meshes, we use a sign distance field representation, an SDF. So an SDF is the mapping of every point in space to its distance to the boundary of a given geometry. So for any part involved in the contact interaction, we can pre-compute the SDF offline. And online, we can query the surfaces of part A against the sign distance field of part B in an efficient way. So that way we can generate contact locations very quickly and contact normals very quickly and use it for simulating contact interaction. Using this approach, we're able to simulate the nut and bolt task in real time, which is very good. Very good, but not good enough for reinforcement learning applications that require generating data at scale. So we want to simulate maybe hundreds or thousands of these phenomena at scale. So we needed more speed up. To do this, we observed that for the interaction, we can generate as many as 16,000 contacts for the interaction between the nut and bolt, which is a lot. But we found that it was possible to still simulate a physically plausible interaction between the parts with fewer contacts. And we came up with a contact reduction scheme that can cluster contacts based on their proximity and similarity of the contact normals. So that way we can go from 16,000 contacts to 300,000 contacts. So using the Gauss-Seidel physics solver, we can, using this approach, simulate as many as tens of thousands of nuts and bolts in parallel. So using the techniques that I just discussed, I'm showing here 1024 M16 nuts and bolts being simulated in parallel in real time. This was 20,000 speed up over state of the art at the time. With the simulator, we can then bring the robot into the scene and simulate complex manipulation interactions. Here, the robot is using a scripted trajectory to pick up the nuts, transport it, and fasten it onto the bolt. So with the simulator, we can now develop or design different training environments to teach robots different tasks. Inspired by the NIST benchmark board, here I'm showing 3 of the tasks that we designed. So on the left, you have the nut and bolt environment, where the goal is to get the robot to pick up the nut from a table and fasten it onto the bolt at the bottom. In the middle, you have the insertion environment, where the robot picks up the USB plug and inserts it into the socket at the bottom. On the right, you have the gear assembly task, where the robot has to pick a number of different gears and mesh them together. So once you have the environment, you can now start training the robots to learn the task. For our purposes, we use reinforcement learning because it's a very flexible and powerful way to learn different tasks. And for the nut and bolt task, we decompose the task into 3 subtasks. so as to make the horizon length manageable for reinforcement learning. So you have 3 subtasks: pick, place, and scroll. Once you have your task, you can then define the Markov decision process for reinforcement learning. Here I list out a number of options, but I'm not going to go into detail today. But ultimately, using the observation, action space, controllers, and reward functions, we're able to use reinforcement learning to solve each of the 3 subtasks and sequence them together to pick, transport the knot, and fasten it onto the bolt in SIM. So we have the behavior that we desire in SIM, but we care more about the real robot. So how do we transfer these policies from SIM to real? In this section, I would highlight 3 of the key strategies that we came up with. One is to use force condition policies that use force sensing for reliable transfer. I would highlight the importance of domain randomization, and also a third method that elicits interactive verification by getting the policy to determine when the task has succeeded by itself. So that way we can transfer policies from the real, from SIM to real. So when we initially took the policies trained in SIM and deployed on the robots, it did not work out the first time. And there are a number of reasons why things didn't pan out initially. I've listed a number of them here. For example, the policies take as input pose estimates of the different parts. So as a result, we need a way to map visual inputs into pose estimates of the individual parts. Because we're dealing with small and reflective parts, this can be quite challenging for pose estimation systems. So the output of the pose estimation system inherently has some noise, some error in them, which get passed into the policy. So we need a policy that can be robust to that. There are a number of other issues like dynamics models mismatch between SIM and real. The calibration can be quite challenging to do very well. There's a trade-off between speed and accuracy of the simulator and a number of other issues. These issues can manifest themselves in a number of different ways. For example, you can have the policy applying, you can see the policy here, applying excessive force while it is trying to execute the task. And it can lead to failure cases that can be quite difficult to recover from, as shown here. So we need a method that can be robust to all these issues to achieve SIM-to-real transfer. For this, we developed Forge, which is one of our recent works that leverages force sensing and has 4 main components to be able to achieve reliable SIM-to-real transfer. First, it uses force observation as input into the policy. Second, the policy is trained to respect a given threshold during task execution, and the user can specify the amount of force at deployment time. Third, we use domain randomization on all the different parameters of the physics simulator, so that way the agent can learn to be robust to parameter misspecification. And thirdly, fourthly, the agent learns to predict when the task has succeeded. That way it can terminate whenever it deems so. So using those 4 ingredients, we're able to train policies in SIM with some level of observation noise. So for example, the actual part is metallic, but the policy input is shown in red. So we feed in a noisy pose information during training so that the agent learns to perform the task even with observation noise. And that way, we're able to achieve reliable and safe transfer of the policies from SIM to real. So using this same force-based SIM-to-real approach, we can learn different skill primitives to assemble a planetary gear system, which I show here in the assembled state on the top left. And we combine a simple motion planner we use a simple motion planner for the free space motion, and then we use the reinforcement learning for the contact with interruption. And here you see different policies for different phases of the task, where the agent can assemble multiple parts to put together this kind of visual system. Just gonna move it along. Cool. So we've seen how we can simulate contact-rich interaction and learn policies in sim, but these policies to the real robot. In this third part and final part, I want to highlight how we can use tactile simulation to improve the policy performance. One thing that you will notice in the videos I've shown so far is that the parts are aligned in an upright fashion with respect to the end effector of the robot. And we observe that when the parts are physically perturbed in a way that requires reorientation of the parts, the agent is unable to recover. And we hypothesize that tactile sensing can be a good way, the sense of touch can be a good way to get the robot to be robust to such perturbations. So in this section, I want to highlight how we do tactile simulation using compliant contact modeling and how we develop an algorithm to enable us to transfer policies, tactile-based policies from sim to real. So to motivate the importance of the sense of touch, an experiment was conducted about 20 years ago in psychology, where you have humans coming to perform different tasks with and without the sense of touch. So for example, on the left here, you have a human trying to light a matchbox with access to all the sensory modalities, vision, touch, audio, and she could complete it, the person could complete it within a few seconds. When you take away the sense of touch from the same person by numbing the fingers, the human begins to struggle to perform the task. And this experiment from many years ago highlighted the importance of the sense of touch for humans, but most robots today do not use the sense of touch. Recently, visual tactile sensors were developed. So for example, here I'm showing a visual tactile sensor and interacting with it by placing objects. You can see in the bottom left what the measurements look like for this sensory interaction. It shows the geometric information, the geometric shape of the object that it's interacting with. On the right is a schematic of the sensor itself, where on the bottom you see what the deformable fingertip looks like, and there is a camera within the finger that is looking at the deformation that happens during object interaction with the sensor. So we need a way to be able to simulate this contact interaction between rigid objects and the deformable sensor. So for this, we want to simulate contact interaction, and then we want to translate the contact interaction into actual sensory measurements, in this case, an RGB image. For simulating contact interaction between the rigid object and the deformable sensor, we use compliant contact, which rather than representing the fingertip as a deformable body, we use a rigid body. But we relax the non-penetration constraints between both bodies such that there can be a level of interpenetration according to a spring damper model. So this manifests itself in the form of, if you have small force, you have small interpenetration. Large force, you have large interpenetration. So that way we can then simulate the interaction between a rigid body and a soft body and measure the level of interpenetration, and use the level of interpenetration as a measure of the applied force. So once we can simulate contact between the bodies, we can have a camera within the sensor to record the depth image of the object interacting with the body. And then we use an existing method called TAXIM to map from depth to RGB sensor. So this is a quick experiment I like to run. We have two rows here. One is simulated and one is real. Can you tell which row is real? I'm pretty sure you guys can tell, but the point here is that our simulator is very similar. The output of the simulator is very similar to what you get on a real sensor, which is very valuable. So we not only simulate the geometric sensing capability of the sensor, We can also simulate shear field measurements, which I show in the top right, that captures which direction the object is sliding as it interacts with the sensor. And in both cases, we achieve significant speed up on baselines. So once we have a way to simulate the tactile sensing, we can then, the tactile sensor, we can then train policies in simulation. For example, here you have an agent that learned to use the sense of touch to reorient the peg and perform the peg insertion task. So for sim to real transfer, we observe that on the robot, you have a number of manufacturing variations across different sensors. For example, for the robot that has 2 fingers, we can see when we compare the left and the right fingertip, we see that the colorations of the sensor are quite different. But in our sim, we only calibrated it against one single sensor. So it's important to expose the agent to these sort of variations during training in sim. For that, we use image augmentation to vary the coloration, so the hue, the saturation, the contrast of the image of the sensors in sim, so that the agent can learn to deal with variations during deployment time. The challenge is that we're learning a high-dimensional policy here, where the input to the model is an image, and reinforcement learning struggles when we're in the high-dimensional space due to cross-dimensionality. So we needed to come up with an algorithm to deal with this. And we came up with this algorithm called AACD that trains the high-dimensional policy in 2 stages. In the first stage, we train a low-dimensional expert that uses privileged state information available in simulation but not available in real. For example, pairwise body contact forces. And it's able to learn an expert policy and critic using actor-critic algorithm. In the second stage, we learn a policy that takes in observations that are available, only observations that are available in the real world, including the tactile image. And so this policy is going to be a high-dimensional policy. So the key insight here is that we can take the critic that was trained in the first stage and use it as an initialization for training the high-dimensional policy in the second stage. And this critic can either be frozen or further fine-tuned in the second stage. So this way we can leverage a pre-trained critic to guide the training of a high-dimensional RL policy. In terms of results, our baseline is able to learn the task that uses just vanilla reinforcement learning, is able to learn the task and achieve about 60% success rate. But using the 2 variants of our method, we see improvements on the baseline. And this is in the low image augmentation regime. As we increase the image augmentation, the baseline struggles to learn the task at all. Meanwhile, our method is still able to learn the task in a very effective way. So that way, we can then deploy the policies reliably in real. So in this case, you have a peg placement policy where the goal is to get the robot to keep the peg in an upright pose. So as I disturb the agent, is reactively reorients the peg by using its sense of touch, using behaviors that were developed purely in sim. On the right, you have a peg insertion policy where the agent can use its sense of touch to perform the task despite acute illumination changes. Cool. A few concluding thoughts. Based on the works that I've shown today, we can now simulate contact-rich interaction much faster than real-time and much faster than prior works. We can simulate tactile sensing faster than prior work. We can use the simulator to learn behaviors for robotic assembly using different sensory modalities, and we can transfer these policies from sim to real. There are a few open problems that we are currently exploring and interested in exploring in the future. For example, we want to develop policies that can generalize across diverse assembly tasks with different geometries. Rather than using one policy for each observation modality, we want to develop, or we're developing multimodal policies that can combine these different modalities altogether, which can hopefully even improve the success rates further to industry standards. And finally, we want to have policies for fixtureless assembly where the sockets do not have to be fixtured onto a surface. This has been a multi-team effort with a lot of collaborators from the robotics team, simulation team at NVIDIA. So I'd like to credit all my collaborators. Thank you very much for listening. I would like to take some questions.
Any questions? I just wanted to ask, in your initial slide, you showed teaching the robot to screw on a bolt. How long does it take to train a policy like that with your robot?
Usually it takes about 8 hours to train it. We train it with 128 environments in parallel. It takes 8 hours.
Thank you.
On a single GPU.
Sorry, question. So when you were able to remove a lot of the contacts, did that also kind of decrease the amount of forces that were experienced because you have less contacts, or were you able to use a different model to model the forces separately to the contacts?
So the question is about the effect of reducing the contact reduction scheme. So we were able to compare the simulation with and without the contact reduction scheme, and we observed that the difference in performance was very minimal. So and that was measured by the level of interpenetration and how much the motion for the parts aligned with and without contact reduction. But and they match pretty well. It's currently an open question that we are also investigating. We're investigating different ways of doing the contact reduction. Today, I presented our approach that uses a notion of clustering. There are other approaches that we're currently exploring. But good question.
Any other questions? Thank you very much, Ireti, for joining us today. Really appreciate it. Thank you. And the BBC as a young pioneer. Thank you very much.
everyone. As mentioned, my name is Beta Hindase, and I am from Ethiopia. Actually, I wouldn't be a good Ethiopian if I didn't say a few words about Ethiopia before I start my presentation. If any of you have met any Ethiopian before, I'm sure they say a lot of these things, but I thought we were the cradle of humanity because Lucy is from Ethiopia. We're considered the land of origins, where coffee is from, where intelligence is from. Our main language is Amharic. I've said that a lot during the past 2 days. And we have also over 80 plus languages in Ethiopia. So quite a diverse country and has a very ancient history. So yeah, I'm from Ethiopia. So I'm going to say a bit about the company I work in, what we've been doing. This is not at all a technical presentation, so I don't have a lot of graphs or numbers, but I'll tell you about our experience and what we've done so far. And maybe we can see if there's an opportunity for collaboration. So, ICRA Labs. ICRA Labs is we claim, at least from our from what we know, is the first private AI research and development company in East Africa. I was actually mentioning this during lunch earlier. We started working on AI before I started being. So this was back in 2013. We're almost 11 years old. So we're focused on AI research, application, and mainly by delivering AI tools and AI development for companies abroad. So how did it start? I'm going to start by telling one of my favorite stories. Does anyone know the book The Singularity is Near? No, not at all. But it's you know, okay. I haven't read it either, honestly. This is the inspiration behind why ICRA Labs came to be. So my partner and currently the CEO of ICRA Labs, Gaitma Tatafa, that you see there. This is a picture of him when he graduated from university at Defense College. So he read this book, The Singularity is Near. And then he wrote about 500 emails to the author saying, I want to bring the singularity to Ethiopia and we can make it happen. Basically, the singularity is a concept of, machines and humans working together to create a very super intelligent machine, basically, in the future. So he wrote about 500 emails. After those emails, the assistant of the author actually connected him to someone that's very famous in the area of AGI. So he actually got to meet the author. I thought I had the next slide, but never mind. But he actually got to meet the author, and he actually also met Dr. Ben Gortsab, who popularized the AGI concept. So after that, that's when ICRA Labs was born. So ICRA Labs has worked on multiple projects across the years. So, so our work that actually put us on the map is our work with Cancer Robotics on Sophia the robot. Basically, what we did there is vision processing and perception software for Sophia the robot. And Sophia the robot is also built on top of OpenCog, which is also a lot of the team at ICRA Labs contributed for. We also have worked on platforms like NewNet, which promote and support distributed computing. We've also done work for Hershey Chocolate, Build Direct, a subsidiary of Sony Music called Runs Music for music recommendation software, and also one of the really projects at ICRA Labs was we were able to analyze the gene data of super sentients so that pharmaceutical companies can use it to make medicine for longevity. So we've had worked on multiple projects at our lab, but since the founding of SingularityNet, which was founded in 2017, our main work has revolved around creating platforms for distributed and decentralized AGI. So there's a huge community around SingularityNet and what they're trying to do. They also have a marketplace that's open source and free for everyone to access. So you're very open to join the community if you have any questions about the platforms or the tools that I just described before. So just a few examples of the ecosystems that are part of the SingularityNet network. NewNet, as I mentioned before, is a decentralized computing network that works on a global scale. And also, because at the core of decentralization is also blockchain, we also have Hypercycle, which is part of the SingularityNet ecosystem. I think one of the biggest also work with SingularityNet is the contribution to the Open Hope project, which is basically serves as more or less a platform to build AGI tools also for robotics. But a lot of this you can learn about on SingularityNet's website. There's also a huge community around it. So if you want to be in it, I think it's very important to have a lot of representation from different parts of the world that be part of it. So this is our lab, used to be our lab. We have our new office right now. This was the torso of Sophia, the robot that we were working on. And we also have these Robo Sapiens. Do any of you aware of the Robo Sapiens? I'll talk about why they're here and what we use them for. So what is my role, right? How did I get into ICOG Labs? So my father actually found out about ICOG Labs, and then he said, you know, there's a company working in robotics. Maybe that's something you'd be interested in. But the reason why is because this is me. I was young. I know I'm just pointing to computer parts, but this just shows that I was very interested at a young age. And I started coding at a very young age. So I was in the Ethiopia's tech scene, teaching kids, but also, building websites and mobile apps. But ICOG Labs was also doing something else. And while ICOG Labs was also building these types of platforms, I was also part of a program called Girls Can Code. Can you see which one? I'm the one wearing the blue jacket. So I was also very passionate about having more people and especially more women involved in tech and also AI. I thought I changed this slide. Okay. Because then, actually, guys, I'll come back to it. But just stop. I'll come back to it. Is it no interaction? Because there's no other stuff. Never mind. I'll come back to the last slide. But the Robo Sapiens that you just looked at there was part of a project that we're doing called the Robo Soccer Competition, where we were encouraging a lot of young people to get involved in robotics and AI. But the problem is, as many of you are aware, and it has been mentioned in the presentations before, is the lack of access to these materials. Especially when it comes to Ethiopia, there's a lot of taxation around it. And to be honest, we don't have a lot of academicians or strong institutes that are pushing for the development of AI and robotics. So as a private company, it was actually difficult for us to do anything, right? Because we're a private company, we work for profit, and we're working with multiple companies. But it was very important to us to also build talent and then build excitement around AI and robotics. So basically what we've done is we tagged these Robo Sapiens. We put Raspberry Pis, and then they had cameras, and then we would do a soccer match or a football match between multiple universities. While we were also doing this, a lot of people were interested. There were a lot of students that were part of these initiatives. So as a result, there were a lot of young people who were interested in AI and robotics in Ethiopia, which also helped us scale our impact, but also get more talent into our lab so that we can deliver more products to a lot of okay, loading. But I wanted to show you a video of how much of the impact that we've made. It is actually 11 years since we started, and this is part of I wanted to show you a few seconds of the video we did based on the documentary we did on how much impact that has had over the years. Sophia actually came to Ethiopia, and then people were really excited. Let me see if I can. I don't think I can play it from here. Oh, it's going to be. So yeah, basically, as you can see, there was a lot of people that came to see Sophia the robot, which was, I think, about, I would say, 300,000 people or more that came to see Sophia the robot. And since then, we have been able to push a lot of interest towards AI and robotics in Ethiopia, but also towards the world about Ethiopia's ability to contribute to the AI ecosystem. Very young. So we started implementing projects under ICRA ACC, and then the impact has reached over 36,000 students and young people across Ethiopia. And we were very fortunate enough to also have some guest visitors, including Jack Dorsey and Mabala. This is also another video, I believe. I wanted to show you some of the projects that we were doing in order to reach a lot of kids outside of the capital using our moving training center called the DigiTruck, which is completely solar powered. It has the Robo Sapiens and 3D printers inside of it, and it would go across, not cities, but rural towns in Ethiopia to give exposure to young people who haven't even seen the computer before. But they're right, their first glance of hope. So let's see if we can. Oh, yes, sorry, you can't.
I don't have access to your Google Drive.
Okay, then I'll just. So, what's next? So, as I mentioned, we worked with companies abroad to build tools for them, the AI tools. We are currently working with Singularity Net on AGI research and development. We have also been educating young kids and adults in Ethiopia to get inspired and be involved in AI and robotics. So what do you think these kids are looking at?
Sophia?
Huh? Maybe, yes, Sophia. Any other guesses?
Ronaldo.
So I think one of the things that I've really noticed is it is very important to inspire people to get involved in robotics and AI. And especially Sophia the robot can help, for example, be an interface between the very complicated or sci-fi-ish kind of science and then the reality. So yes, these kids are looking at a robot, but it is another version of Sophia the robot that we worked with Hanson Robotics with. And this time around, this robot was speaking Amharic, the federal language of Ethiopia. So there's also another video on YouTube you can play. So this is Desta, the robot, which actually played or performed with Ethiopia's very famous musician called Dr. Mulatu Astatke. I don't know if any of you have heard Ethiopian jazz. No? No? Highly recommended. So this was kind of also a pinch me moment for me because Dr. Mulatu Astatke is very famous. It's one of the musicians that I really admire. So having people come in to actually see a robot performing, performing in a sense of she spoke a poem, but also she moved her head and her hands while he was performing, which was fun. But can we play the music? It was okay.
Complicated.
But either ways, this was also something that was really broadcasted across Ethiopia. A lot of, I know this is a lot of, I don't know the right word for it, but this inspired a lot of people and also encourages a lot of people to pursue AI and robotics. But during this process, what we've understood is we also have to build things that look like us, but also speak. So go to, I'll just send the links wherever I can send them to. So yeah, we are introducing a new strategy shift. As you, ICRA is now focusing more towards building local tools and using local context. So basically, we have learned a lot from partnering with a lot of organizations abroad. We haven't, we have experimented on building and implementing AI on local projects, but as you know, a lot of problem around computational power, but also talent, but also data, right? But right now, I believe that we are better positioned to build local solutions using the knowledge that we've gathered so far. So right now, we're actually working on a platform called Layu, which translates to identify in Amharic, to crowdsource speech data sets across Ethiopia, which will eventually help smallholder farmers and health extension workers to access information. Digital literacy, but also literacy on its own is a big problem still in Ethiopia. So with this, we believe that there's a lot of things that we can solve. But basically, this is our journey. We're excited to be implementing Layu and possibly other projects along with it. But yeah, thank you so much. My name is Betaling Dese, and if you are looking to collaborate or work with us, this is no. Thank you very much. Any questions?
About the remote lab setup that you mentioned, where you do you have trainers that go with into the rural areas to teach the students?
Yes, I do. I don't know if it's possible, but maybe to visualize it, we also have a video on YouTube. But it's so the reason that we did this, especially in Ethiopia, the problem is there are not enough centers for people
VR applications. And today he's going to speak to us about human-computer interaction.
For full surprise, I managed to mention my name exactly. Yeah. A lot of people struggle to say it. So they would say Wi-Fi, some people call me Wi-Fi. Yes, as much as possible, I'll try to finish very early. Just realizing that my spelling of university is wrong. It tells me that I'm very, very tight. I don't know when I'm tight. We'll try to do it this one. So for today, what can do? Flip it. So I'll give a little background about myself, where I am, and then persuasive computing. I believe it might be new to some of you, so I would want to give an understanding of what persuasive computing is. And then what we are doing at the ACI lab at the University of Ghana. And then we hope that out of this, we may get some collaborations, because I've heard a lot of things that people are talking about that sounds very interesting, that I see how we can bring some persuasion into it and then make it more interesting. So I did a PhD in informatics at University of Reading. Originally, I started as a mathematician from the Kwame Nkrumah University of Science and Technology in Ghana. And then I went to UK to do my master's and PhD in informatics. And then I specialized in persuasive technologies. And currently working at University of Ghana at the Department of Computer Science. So that was the University of Ghana, very green from the top. Sometimes when I look at the picture, I don't really believe that it's that green. When you look at it from the skies, it's very, very green. It has a lot of traditional buildings built by the British. So we're still maintaining the heritage. We still believe that if you want to put up any new structure, the architecture should form within this type of building. So some of the buildings are relatively new, but they are deliberately built like that to fit the architecture. We have about 60,000 students, and it started before independence in the 1940s, and it was before the College of Linguists. And we are located at Legon. So Legon translates to Knowledge Hill. So the name generated from the establishment of the university is on top of the hill, and knowledge, that is so Knowledge Hill. Legon. That's where you find us. I don't know whether there's anybody else been to the University of Ghana. Fantastic. How do you find the place?
It's very beautiful.
Yes. So we have staff population. We have a lot of, sometimes when I see the numbers, I don't really believe it. We have about 2,000 teaching faculty. And we span across, we do a lot of things at UG. I don't know everything that we do. I don't even believe I know a quarter of the staff. So persuasive computing, what is persuasive computing? Around 1997, a gentleman in Stanford University called B.J. Fogg came out with the concept of persuasive computing. He started as a psychologist who moved into computer science. And then he came out with a concept that we are moving towards an era where we should let computers do the persuasion instead of humans doing the persuasion. And I can tell you that it is with us. It's just that maybe we are not aware. As I go on, you see that we're doing. Now, when you pick a computer, it plays three key roles, right? It serves as a tool. We all know that computer serves as a tool. It's also coming out as a social actor. Now, social media is there. Everybody is on social media. And it also serves as a medium for communication. But there are other properties of computers that makes it very, very interesting to work as a persuasive tool. For instance, we accept computers as places where we normally not accept any human being. So if you're on the toilet, I think a lot of us do this. We go there with our phones, and if you are not careful and you behave like me, you can spend an hour on sitting on the toilet, forgetting that that was the reason why you got there. You're still flipping through Instagram, WhatsApp, and all those things. Now, for us in persuasive technologies, we think this is an opportunity where we can get to you at the opportune time where you will not even be ready to talk to any human being, but we would be able to persuade you. For instance, if you look at those wearing smartwatches, Apple Watch, Samsung, Apple has a technology they call the rings. So when you get up and then you start doing your daily activities, it prompts you that probably you've not been standing up a lot of times, and then it will vibrate and it's about time for you to stand up. If you use Nike Plus, it tells you Runtastic, it tells you try and do some more physical activity and stuff like that. I don't know whether you've been following it. or you've not really been following it. So it's something that has come to us, and then we use it. Now, if there are some modern cars, I don't know whether you've observed that when you are speeding or you are driving harshly, the dashboard turns red. And then when you are driving economically, it turns green. There are some showers that has been designed that when you are taking a shower and you are wasting water, the water looks red. There's a red light in it prompting you that you are wasting water. So these are simple technologies that are being used. In terms of robotics, this is something that was done in the US. So they designed babies as robots. And to prevent teenagers from getting pregnant at teenage age, they give these babies to them. The babies behave like real babies, these robot babies, that they wake up at dawn and they will cry, and you need to feed them before they stop crying. And then when you feed them, you need to tap the back like mothers do everything. Now, when they tried this over a period of time, all the areas they experimented, teenage pregnancies dropped. Because they started realizing the challenges of being a parent. And that was the reality. So that is how these things go. I think we see it a lot in Netflix when we're having recommender systems and all those things. It's a form of persuasion. Amazon, you buy something and tell you 70% of people who buy this also bought that. And you wonder why. Sometimes you check and it relates to what you really want to buy. And these are some of the things that are going on. I quite remember some of the research that we are doing. I'll be talking about some, but one that I forgot to put there is we were trying to look at impulse buying within virtual spaces. And we realized that, yes, people, you can put persuasive concepts within virtual spaces that will make people buy a lot. So they can be applied in all these areas: health, well-being, e-commerce. Please, am I talking too fast? I'll finish it. E-commerce, environmental issues, energy saving, education, security, and what have you. So if you look at it, you can see that the opportunities are there. When I sit and I listen to stuff that people are talking about in robotics, and I'm seeing a lot of connections here that we need to start looking at whether we can connect these things to. Please come. Okay. I kind of like this because I think it's the simplest illustration that we can have, that you can actually make people change the way they do things. Now, for us at the HCI lab, we do things similar to this. We try to encourage people to do things that they would normally not do using simple technologies. So let me start with what we call persuasive spaces. So in 2018, myself and Agnes Tibe came out with the concept of persuasive spaces, that is designing spaces that would make people change the way they behave, right? Now, when you look at intelligent spaces, we have intelligent spaces. So intelligent spaces, the building would change, or the space would change its features to suit the occupant's behavior. But when it comes to persuasive spaces, we are doing the opposite. We want the behavior of the person to change to suit the intention of the space. So the space will be designed with a specific intent. And then based on that intent, we will make people behave. Now, imagine doing this in so we started thinking about coming up with anger detection and suppression. And we were thinking about spaces in cars. So let's see how this one will work out. Like, we all know what happens in cars, all of us. I don't know anybody who drives and you've never gotten angry over this. Certain things, if you don't get angry, then you are not human. But the point here is that our concept is not to stop people from getting angry, because it's a normal thing. But we want to detect anger at its early stage, and then we'll see how we can persuade. So we started this project. We made some headway. We got to a point, and then the fans, because I think last I was telling some of my colleagues that the problem we have in Ghana is that every research you see, about 90% of the research we do in Ghana, we fund it. No one funds it. So when it gets to the point where you need a lot of resources, then you have to pause if you are not getting donors. But we managed to get to the point where we detected that we will be able to detect anger using facial recognitions and then, facial expressions. And then we can suppress anger using music with some soft tones and things like that. We will be able to suppress anger, but we're never able to implement it in a very physical way. Apart from that, we also came up with intelligent road marking. So persuasive and intelligent road marking. Now, what this road marking we did with it was that we came up with an Arduino Uno board, and then we program it in a way that it's lights on red and green based on the speed of a car. And then we arrange it on the road to form a road marking, road divisions. And then it's controlled by the speed of the car. So when you are over speeding, it turns red. And then when you slow down, it turns green. Now, when we finished the project, we were struggling at that time. We needed money to even buy a 3D printer to print the components to put it together. I didn't get it. So we decided to test it in a virtual space, right? Because we also do things in virtual reality, and we got some interesting findings. So what we did was that we developed a virtual space, two virtual spaces. One is a hypothetical virtual space, that's the one I'm showing. And then we developed one on the UG campus area. And then we set up a driving simulator. And then we made people drive through the environment with the same features. So you could see the line turning red because the person is speeding. And when the person slows down, it turns green. And so it turns white. Now, what happened was that after this study, we realized that people who were driving on the unfamiliar areas were actually obeying this thing very well. Those who were driving within familiar areas were still overspeeding. But then there was one particular thing that we saw with when they were slowing down. Now, a lot of people did not actually apply brakes. They only left their hands off the speeding pedal, the accelerator. So it kind of made us feel that it is an opportunity that we can explore more to see how this thing can be physically implemented. We went on with the version 2, which we actually put into forms of road stalls that were supposed to be tested. We had some talks with some of the people within the transport industry in Ghana, that's the Ghana Road Highways, trying to see if we can get funding, but nobody was ready to fund it. In some cases, we've been told that we are too futuristic. Then, with regard to virtual reality, we've also been doing things. So like I said, we look at persuasive spaces. So we are talking about physical spaces in terms of persuasion, virtual spaces in terms of persuasion, and we want to understand human behavior and see how we can change things. We conducted another study in virtual spaces where we looked at virtual learning, right? So we've heard these things about a lot of issues about using VR to teach, YouTube. I think during COVID, we were using YouTube and all those things. So we decided to conduct an experiment to really test whether these areas or these platforms are really good for learning. So we picked
a physical classroom, selected students of computer science departments, and then we found somebody from humanities to teach a topic on globalization that we believe that a lot of them have no knowledge about. Then before they started, we used an RCT, a randomized control trial. We split the group into 4. And then before they started, we gave them a prior test. So a set of questions, everybody completed it. And then we recorded how they performed. Then they had a lecture on that same topic that they've completed. Then when they finished, we then gave them the same questions to see whether there's been some learning. Now, the 4 groups that we used, one group was those who were in the physical classroom, and then we designed a virtual classroom that mimicked exactly what was happening in the physical classroom. We superimposed the audio, the voice of the teacher, everything in this environment. And then we let the students go through the virtual space and then did the learning and then did the task afterwards. We did a similar thing with augmented reality where we superimposed the sound and then use an augmented reality. Then we did a YouTube video and then we compared the 4. Now, when we finished, we observed that the physical classroom outperformed all. The student, it wasn't as if there was no learning. In all cases, there was learning, right? Which means that all the platforms are good for learning. But then we observed that students within the physical classrooms did better. Now, 3 things. We tested the first 3 levels of the Bloom's taxonomy. That is knowledge, understanding, and that kind of thing. So there is a possibility that when we move to the last 2, analysis and synthesis, probably they might do better with a VR environment. But then for the first 3, where the focus is purely on knowledge and stuff like that, that was what we saw. We also believe that it is probably because the pedagogy skills or the pedagogy that was used in the physical environment has been transferred to virtual environment, which means that when we are doing things like this, when we are moving on to virtual spaces, we should be careful the pedagogy that we use. If we cannot adapt the same 2 sets that we use in the physical environment and then do that, because in these settings, what happens is that students sit in a VR environment, you see the classroom, lecturer is speaking to you like we do. And we saw that that probably did not do very well. Then the last bit of work that we do is to do with human-computer communication. Now here, we've been interested in things to do with this. I think Ekon will be talking about investigating how the format of a communication will impact how people will accept something. So we've been looking at text, real voice, and artificial voice within a virtual space, whether the level of acceptance. So I'll leave that because he's going to talk about that. Then in terms of large language models for low resource languages, again, we've seen that majority of the systems, and I think it was only the last speaker who mentioned robots that were speaking a local language. But in most cases, the languages that the robots are speaking are English, French, the well-known languages. But then, what about the ordinary person in South Africa who cannot speak these languages, right? And that is where the problem is. And as I move on, you see that those people are really waiting for the technology. It's just that we are not giving it to them. So we decided to work on that. First of all, we realized that there is no data set in if I know Ghanaian language as a data set that can be used for anything. So we spoke to Google, and they were willing to help us. So they funded us on that, and they made us collect 5,000 hours of 5 different languages in Ghana, 1,000 hours each. And that was the project that ended up giving me a lot of gray hair. Please. And let me play this video. So the biggest challenge when we started this project is that we even recognized that or realized that our language is vanishing. It was so sad. It's vanishing. Now, I am an Akan, right? And it's the largest speaking language in Ghana. And we were surprised that the Akan language is so diluted that about 40% of the language is now English. It's serious. Like when we, it took us a lot of energy to get the actual dialect, because when people start, and I'll show you when we started doing the ASR model, so you will see that the language is actually full of English. And that is one of the biggest challenges that we are having in training these models. So we started by, like I said, we have 5 languages that we're focusing on. ICRA is almost dead. That's the last language. ICRA is almost dead. And the people were really, really happy to see us there. In fact, even their chiefs and things all participated in the data collection, because they said that it's something that is out there. Then what happened was that we tried, like I said, 5,000 hours, 1,000 hours each. And for each audio, we were targeting between 15 and 30 seconds maximum. We developed an app. And then what we did was that on the Android app, we people have it on their phones. So we distributed phones to people to use. And then we have about 1,000 images. And then you look at the image and then you describe the image in your own words in the language that you speak. So through that, we collected about 1,500 unique voices per language. So for each language, we recruited people to that number and then we recorded from them. So you could see how tedious the project was. And then we had 50 categories of images, right? So health, agriculture, to make sure that we are capturing the diverse part of the audience. And then we finished and we make sure that for each audio that has been recorded, we have 2 native speakers who actually listen to the audio and validate, confirm that what they've said is actually what is there. And that was where we started seeing the problem. So people were pronouncing wrongly. That was where the only time you get people saying it correctly is when it is an English word. Majority of the time, people were pronouncing things wrongly. For instance, sorry, you don't understand, but you may get when you say men in Akan, right? Man is Berima. That starts with B, Berima. But then when it is men, it is Merima. There is no B anymore. But then we realized that a lot of people were saying Mberima, which is completely wrong. And so at a point, we have to speak to some linguists, and they said that the only thing we can do is to adapt the new forms of the language. So it means that we realize that the language has changed completely. And if we don't, then our data wouldn't make meaning at all, because this is how people are speaking now, and these are the new words that they have formed. In fact, we kind of agree with them, because even when you look at English, the words have changed, the pronunciations have changed. And so maybe the language is growing. That's how we should accept it. It's just unfortunate that most of the words are becoming borrowed words. That was where we have issues. So we did that, and then we also, the app ensured that anytime you have more than 3 seconds break in speaking, then it rejects it. But that has led us to something new. We've seen that there are people with speech impairments. So it means that by default, our approach of collecting data was discriminatory. So we've started another project where we are targeting specifically people with speech impairment, because else they will not be able to use these models that will be coming up. Now, the data set is open source, and that is a link I can give you to anyone who is willing to play around with it. We have the transcriptions, so you don't really need to understand the language. You can use it to play around and see if you can train your ASR models. Now you could see how people were. This was a very fascinating experience for us, where we got to a point our internet connectivity was not working. Now, even though the system doesn't need internet to operate, our initiation of this app needs internet. So we get to places where internet was not working, and we would tell the people to go home and come the next day to record, and some will sleep. So this lady actually refused to go home. She said she's traveled about 3 hours to the place, and then she won't go back. She will sleep and wait till the next day, and then record it. And for us, that was where we saw that this is a big thing. In fact, majority of the people, we were thinking that they have nothing to do with technology. And then when you explain to them the importance of they having their language, and all of them were for it, that they keep saying that there are times that they can speak to their phones, and their phones will do stuff for them, and they cannot. So it's anything like that, they welcome it. And honestly, it was an eye-opener for us. So what next? Now, what we've started doing is that we have started developing ASR models and TTS models for local languages. We started with Akan, and then we are also looking at how we can come up with this data set. We can actually come up and train a model called Obapenyi, that is an elderly woman translated, a chatbot that will support antenatal care. And then we are also seeing how, like I said, we can expand the data for other. So for now, this is what we've managed to achieve. We're using Whisper, and we are using the Yoruba trained model because the language is similar to Akan. And this is what we've achieved. Now, the challenge here is that you could see that our word error rate is quite high, but it makes sense to a point for us. The reason is that there are 3 dialects of the Akan language. We have the Fanti and Asante, a stream end, and the Kwiapim in the middle. What we realized the model was doing was that because people were speaking these 3, when people write Asante and it is training, it ends up writing in the Kwiapim. So it's writing the one in the middle, which for us is fine because it's readable. Any Akan person can read and understand. So it means that it's okay. Maybe moving forward, we'll try and then separate the 3 languages, the 3 dialects, and treat them as each. But if you look at it now, look at actual transcription. So this is where I even said the machine was doing better than humans. Actual transcription, I don't know whether I can see the word rubber. So as for rubber, and it's rubber. And these are expert transcribing people. And they are even writing the English word rubber. But then you could see that the machine said rubber, which sounds more, even though it's an English word, but it sounds more Ghanaian than rubber. So actually the machine is more Ghanaian than Ghanaian. So we saw this out. I mean, it was all over where, for instance, FPDA, this one is FPDA, but spelling is wrong. It's FPDA. The machine was actually doing better than humans. So we kind of happy. We think that, so collaboration, like I was saying, for us, and hearing the things that were going on, I started thinking about, should we get to the point where robots will be speaking P? It will be very, very fascinating for Ghanaians to go to areas, and that will make them accept it. That will make them accept it. I remember when I was young, about 90% of programs on TV were all in English, and people were not happy about things, and they don't even care about anything. Now, about 90% of our radio stations are speaking local languages, and I can tell you, if you go to the ordinary person, a Makala woman who is uneducated, and you try the person on American politics, she will embarrass you. They know more than you think they should know, all because the information is given to them in their local language. They know more. If you see an ordinary Ghanaian who has not even had any good education, talk about South Africa, and you'll be surprised the things the person will be telling you, because they get the information right in the first language. So we think that when these things come, when we start having, they will start accepting robots. When they see robots speaking, it's a cultural thing. They see robots speaking their language, then it makes meaning to them. Again, another thing that I gathered, I think yesterday I was speaking to some of my colleagues from South Africa, and then we were doing a lot of hand gestures. And I realized that there are some I can't do here, that they say if you do that, it's serious. Meanwhile, in my country, if you do it, it's fine. It's you could see that the same thing if you do it. And I was asking that if I do this in my country, it's an insult just by doing this. But you do it here and it's fine. And these are some of the things that I think, as we think about the interactions between humans and these robots, we should start considering. Because if you are not careful, people will misinterpret everything that the robot is doing just because of a simple gesture that it's doing. So some of these things, we think that it's about time we start thinking about collaborations. For those of you in the robotics and those of us in the HCIs, start thinking about research that will bring these humanized things, how cultural things into these machines. Thank you very much. And any questions? I did 20 minutes, right? Or more?
I have a question. So thank you for the talk. The first example that you showed of persuasive computing, the staircase thing, piano, I understand it's very interesting initially, but over time people will stop using that, right? So how do you make sure that people continue doing something?
So for now, yes, I agree because of autonomous vehicles. So the possibility that people will even be steering is going to be out. When it comes to driverless cars, people are speeding. But I'm pretty sure that this is not going to happen very soon. Now, if you look at the technology and the autonomous vehicles, the way it's going, it looks promising. But the issue, in fact, that was one of the things that we also requested for grant to test, and we never got money. The issue of trust and ethics is a big thing when it comes to autonomous vehicles. For instance, the famous dilemma issues, the trolley dilemma, where an autonomous vehicle needs to make a decision between hitting an elderly person and a young person. And these things have a lot of cultural implications. So, yes, we believe that the technology is ready, but the issue of acceptance is because can you trust your vehicle if you really know that in cases of accident, it will crash you because you are an elderly person than the person on the road? Immediately, people start having a second thought about whether we should really use these cars. So the technology is there, it's fine. But we believe that at least within the next 5-10 years, it's still relevant that we see how we control behavior in cars. But as for any technologies with time, when it fades out, probably persuasive technologies may not be necessary anymore at a point in time. Yes, please.
Hi, Prof. I wanted to ask whether your study with the road marks considered adding like a second color to it. For instance, a driver would see maybe a color orange warning them that they're exceeding or they've reached like the speed limits, and then they would put like they would not accelerate anymore, and then maybe a red color would force them to actually stop, and then it would change.
We got this in one of our presentations, and actually, like I said, at the point we stopped. But the future for us was even to move to the point where road markings would rather communicate driving instead of having traffic lights and things like that. Because when you are driving, what brought into this thinking was that when you are driving, your eyes will be on the road. So if we communicate to you on the road, then we are doing a better job than making you look up. So supposing we are able to even, to add to what you're saying, we are able to even control traffic lights, junctions, how people should move at a junction, control your speed in a way that by the time you get to a junction, the intersection, it is free. Then we will make a good headway. So for now, yes, what you are saying is 100% true. But like I said, we stop this. If there is a lab here that will be willing and they have the things to support us to do this, I am really for it. I would really, really be very, very happy that we continue with it.
Right. Quick question. On the teaching front, so obviously you found kind of for that context, in-person teaching outperformed. For the other options, what was your impression of different options kind of?
So the first was physical teaching, second was augmented reality, then virtual reality, and then YouTube was last.
So what was the AR setup? Like how did that work?
The augmented reality. Yeah. We used how do we call this thing? Tablets, and then we impose the image on the screen. So when you sit in the class and you hold it like this, you see the others in the classroom with the lecturer on the screen on the same interface.
There are no more questions. Thank you very much.
Thank you.
So I'm just going to introduce the last speaker. So this is Akon Obu Ekpezu. She is at the University of Ulu in Finland, and she is a visiting researcher at the University of Ghana, working with Prof. Isaac. Thank you.
Good evening, everyone. My name is Akuna, she has rightly said. My research area is just a little niche of what Professor Yafi is doing. And I'm looking at, so we have persuasive systems, right? Applied to different areas. They have been established to be effective. Then, how long do we continue using the system? What are those things that will make us continue using the system? Initially, we all get very enthused about using it, but at some point, the compliance rate begins to reduce. So amongst that's the broader research area I'm looking at. But specifically for this presentation, I'm interested in communication channels. What communication type or strategy would influence people to accept these systems more or follow instructions from these systems? So we look at background, study design, and findings. So the main research question here is, what is the most effective communication channel? We're looking at different communication types, the richer media, the linear media, the persona of the communicator, human-like, robot-like. Would it take the persona of a female communicator or a male communicator? Would it be voice? Would it be text? Which one would actually influence you to accept or use or accept instructions from these systems? So to answer this research question, again, just to recap, we are looking at communication strategies. So yes, we had to design a message. Usually when you're using your systems, you get maybe a prompt or you get a reminder. It could be in any form. It could be as a text message, it could be as a voice. That's if you activate that on your phone. But then for this message to persuade you, it has to have certain principles. And we looked at the Fox behavioral model, which says that for the message to be persuasive enough, it must have three principles. It must be motivating. It should have the ability to, it should have ability and then trigger. So by motivation, for the purpose of this study, motivation here, we leveraged on social norms. Social norms being that if you know about the behavior of your friend, that would likely influence you to do the same behavior. By ability, we are just telling you that, yeah, the efforts you need to do this is very, very minimal, but the benefits are huge. And then the trigger, which is a call to action. So you know the benefits, you have been motivated to do it, and then the simple cue to action, are you ready to do it? So to test this, we developed two environments in virtual reality. The first two environments with two activities and two communication styles. Now, in the first environment, it's what we have down here. Sorry, I went too far. Okay. This was a movie room where you're supposed to do a passive activity. It was in VR is simply a simulation of real life. So what you would normally do in your everyday activity. And we assumed that when we are free, most of us like to watch movies. And so we designed that environment. And then the second environment was a VR gym. This was actually designed to replicate a physical gym in University of Ghana, where the study participants were run from. And then we used two communication styles. Just thinking, I think we would test this on us here. I would not review the communication styles. I'll let us be the judge and then determine which one would be more effective. All right, now this is a study design. So we have the environment, the movie room. You're supposed to receive 4 prompts to perform a physical activity. That is while watching the movie, which is how the systems normally work in real life. So you're reading or you're doing whatever you're doing, and your Apple Watch would maybe prompt you to get up, maybe take a walk or something. So you'd get the first prompt at 5 minutes into watching the movie. Again, you're at liberty to accept the prompt or continue watching the movie. If you continue watching the movie, have a second prompt at 7 minutes. If you again ignore it, you have another one at 10 and then another one at 11. Now, considering that it is VR where you cannot actually stay there for too long, the chances that you feel exhausted, it would increase your cognitive burden. We used movies that span for just 11 minutes. And if you also choose to go to the gym, now for persuasive systems, the key thing is that it is supposed to influence you to do something without force or coercion. So it's supposed to be voluntary. So even though you would get the prompt to go to the gym, you can still decide to exercise or not to exercise. And that's where we have the click to start or to quit. Now, if you decide to quit, then the system will prompt you, okay, you have 2 or 3 more exercises to do. And then you would still have to choose or confirm, okay, yes, I still want to exercise or want to quit. So we had the study design, as I said earlier, we began with watching a movie. So when you put on your Oculus headsets, we had a list, a predefined list, which we had already incorporated into the VR. So the study participants would choose any from the list. Now, this participants chose a cartoon. They're just going to play the last few till we get the prompt. And this is the prompt. I don't know if this is clear enough for us to see. Okay, this was one prompt displayed as text within VR. Okay, so let's conduct the experiment here. This would be our control group. You got the first prompt, which was text, and people over here would get this, the voice prompts. Okay, now for those of us here, how many of us would choose go to the gym? 1, 2. Okay, now for those of us here who received text prompts displayed on the screen, how many of us would go to the gym? 2.
I think I just go to the gym anyway.
Okay, interesting. Now, when after conducting the study, we had about 260 something participants, and this is a surprising thing. Now, here we had an equal 2-2, right? Now, from our findings, now in case you decided to go to the gym, this would be the gym. I'll skip this. Now, this is what we found. Those who received the text prompts displayed on the screen actually, obeyed or went to the gym, or they did better than those who received the voice prompts. Now, what does this bring to mind? Remember that we are looking at communication strategies, how effective or which one is more effective when delivering these interventions to us. In this study, the voice prompt was originally a female voice. We had one of the students in the research lab do the recording, and then we automated it to a machine voice, right? And then, of course, the text was a normal text. So it brings to mind that this should actually be the next phase of the study, that we would actually have to test for the human-like voice and not the machine voice, right? So now we have results for text, we have results for the machine voice. What will happen if they have the human voice? Okay, and there are also different areas to it. Would it be the male voice or the female one? Whichever one work better. It's still a work in progress, and so far, these are the results. Okay, thank you. Okay.
So my question is just that when you were doing the experiment with the text and voice, right? I know that for myself, sometimes when I just say okay, just click okay, without really, thinking of what's there. I know it's common for a lot of people. So, do you conduct an after survey of those who actually clicked on going to the gym, whether they actually wanted to go to the gym, just click on the prompt just to get it out of the way or something?
Yes, we had a post-intervention or a post-experimental survey where we actually asked both open-ended questions and closed-ended questions. So, did you go to the gym? Was the message how motivated did you feel to go to the gym? If you went to the gym, why? Those were the open-ended questions. And then, of course, we had the structured questions and all. And then, even within the environment, there was a second phase where even though you would choose to go to the gym, you have another cue. Are you ready to exercise? Right. Then you have the option to choose start or quit. So there was a double phase of, the prompts. Now, if you also choose quit, there's another phase which asks you to confirm. Do you want to quit? If you say yes, it will tell you, okay, you have so and so number of exercises left. Do you still want to quit? So that was supposed to draw your attention to not just clicking randomly.
Experiments. Have you tried like maybe for the voice thing? For the voice prompt, could you try? Have you tried using the male version of the voice?
Yeah, that's why we said it's a work in progress. That would be another person I would be testing.
Human then.
Yes.
Because I, for one, I would have
gone for the female person.
The male voice, like the male voice is.
Okay. Yeah. It's a work in progress. So
the voice is male voice.
This is actually a male voice. It was done by female in the physical world and then automated to a male voice.
Yeah.
Yes.
So because you're using the VR and it's a variable, maybe you can sense few other things like your blood oxygen level is decreasing, exercise will be good, or give some feedback about the health of the person. That might persuade more people to go for gym option.
Okay, yeah, that could be another strategy that we would consider in the persuasive message. For this one, we just kept it simple. It would improve your mood. So we could consider that as another strategy.
How many people were in this study?
360 something.
Okay.
Evenly distributed. I think those who received the voice prompts, we had slightly larger than those who received. So I think it was 138 to 130.
And then you said that the ones that received the text, what is the number there though? What percentage?
Percentage-wise, we had 82% of them accepting the prompts.
After at least once during the 11 minutes, yeah.
And then for those who received the voice prompts, we had about 72% of them, right? Now, statistically, the effect size is not large. Even though it's statistically significant, the effect size we currently have with these findings is considered small. And that's why there's need for us to move forward with the study with other personas.
And then I know the theme to go to the gym is just like a virtual thing. It's not like an actual, you have to go and run on a treadmill or anything like that. But was there any consideration in the level of how active people were in the particular different groups? As individuals, if they were regular gym goers as perhaps maybe.
Let me talk a little bit about the gym parts, which I left out. We also had predefined list of exercise sets, which was supposed to go progressively. So the first two was 20 seconds, and then the last two, 30 seconds. So it's also a persuasive strategy, which it's called tunneling. You introduce the task to the people gradually, and both groups had the same task as of when they decide to go. Now, if you accept the first prompt, right, compared to someone who accepted the last prompt, someone who accepted the last prompt will do the 30 seconds exercise, and someone who accepted the first prompt will do the 20 seconds.
But my question's more was there any like study or comparison done to filter out people's just preference to maybe going to the gym or doing these like virtual gym activities versus their preference to watching a movie? If that makes sense. Because if I have a higher preference to going to the gym, I'll just, click that instantly. I don't care what the prompt said.
Okay.
But I want to go to the gym rather than watch this movie.
Okay, so
that's why I'm just wondering, in the study, did you like ask or like,
to get it clearly, say before the study, did we collect data to know people who are really physically active and those who are not? Is that what you mean?
Yeah, or in this like virtual environment, people who prefer to watch things versus people who prefer to do the gym game.
Okay, we actually have data on that, which we are yet to analyze.
Okay.
But if I may contribute, if you use an RCT, a randomized control trial, then it should take care of that, because you evenly distribute people to treatment. So there is a possibility that there will be similar characteristics in the other group, and your statistical calculation should be able to take care of that. But like he's saying, we did a pre-test to know where the people were before they started the intervention, so that we can tell whether there is actually a change.
It's quite cool. Is there an intention to perhaps have a third control group that receives no prompts but can choose to go to the gym anyway? I'm interested to see that.
There is.
So when mobilizing participants and group, you consider factors like age and stuff like age and gender.
What Prof said answers the question. We randomize participants. Before we do the main analysis, we check for differences between groups. Maybe there was any bias, right? And for this study, the analysis we've done so far, there was no bias. There was an even distribution of males and females, age-wise, and all of that. So we did not find any statistical difference between groups in terms of gender and age. Majority of the study participants were undergraduate students. That's another thing I forgot to mention.
And if I may come in again, now if you observe what we at the HCI, what we've been doing is that we adopt this RCT because we believe it's very, very robust. And I think it's some of the things that we can all be using, because that's what they use in medicine. So before they introduce a new drug, because they want to be 100% sure that the drug is effective, they use RCT. And then they take the population, get a sample, the representation is even. When you use RCT to evaluate anything that you've done, it is very, very difficult for somebody to argue that your findings are inaccurate, as long as you follow the procedure, because these are very robust statistical methods. So that is why you see that most of the time when we are doing it, because we believe it's an intervention, it's going to change the behavior, then let's use RCT so that we can argue more rather than just picking. So she simplified the whole process, but it's a whole, we have to calculate effect size. We just don't sample. We calculate the effect size. So what type of sample will make a true representation? We get that. Then we take care of non-responses, biases. We take care of all those values to make sure that whatever findings we get, we can generalize it, just like they do in medicine.
Okay. Thank you very much. Thank you.
Everybody, that concludes the program, well, the spoken program at least, for ICRA Africa. Thank you very much for being here. I hope you enjoyed it. The bus will be here in about 10 to 15 minutes to take everybody to the main campus so that we can go have a tour of the rail lab. Cool. Thanks.